new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials, and present research findings to scientists, ensuring safety and quality standards are met. our radio. We have our own radio station that provides information to the citizens and people at Katarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.
A laptop is an essential asset in the modern society. However, many of them are lost as a result of theft taking with them vital information. But now comes Tracker, an online system that gives users the ability to register various electronic devices using their serial numbers. To access Tracker services, visit the website, create an account, log into your account, register the device serial number. In case your device is stolen, you report in the portal. Tracker will then help you track and recover the device.
I had lost my laptop, but thanks to Tracker, I found it. Asante sana
Tracker helped me track and recover my lost laptop ikiwa na wewe pia jaribu Tracker cause iko vipi.
Wait, let's take our cylindrical lens. So I'll show you this one. So this is a cylindrical lens. I want, maybe you can have a look. So you see, it's I don't know if you can see what I want you to see, but here it's flat. Okay, this side, can you see that it's like a cylinder? All the efforts, can you see that it's curved only in one direction? You can see, right? Okay, it should be quite obvious. Can you see? So you don't touch the lens. Now I have your fingerprint. Can you see the fingerprint? So that's bad because you have everybody has oil on the skin, which is fluorescent. So if we are working with fluorescent, we have to avoid as much as possible to have contaminations. And also this can, destroy a little bit, not destroy, but like everything is very, the coating, everything is very precise. Now there, where your fingerprint is, What will happen to the wave front of this, of the, so, no, very bad. So, the thing is also, you would say, well, just clean it. It's not that easy to clean it, huh? You need cleaning tools and then specific products, and sometimes some of the optics have coatings that you can damage if you clean. Okay, so for example, if you have a dielectric mirror like the one that we were talking about today, when the other lady that was talking about compression with the dichroic mirrors, with the multi-layered mirrors, those mirrors are really expensive. You don't want to get them, like, you don't want to touch them. You just stay away from my dichroic mirror. And if you try to clean them, I mean, you might ruin the compression of your pulses, so it's really something that you shouldn't do. Well, now it's done. Yeah, exactly. So I'll show you. So if I mount here this lens, okay, this mounting that I have placed here, it is a mounting that can rotate. Okay, so let's see what happens. Okay, first of all, let's check with a piece of paper, so we check in a controlled way. So I'm here, I'm very close to the lens, and there is nothing to see. But if I go in the focal plane, look, I have a line. Can you see? So the focal plane of this lens, it's a spot, it's a single dot. Here, the focal plane, it's a line. Okay? Why is that vertical? Here it was round, here it's round. Here it's horizontal, and over there is vertical. First of all, if we think of this in 3D, it's a plane. Look, you can see the plane if I do this. Can you see that it's a plane? Yeah. Okay. If I rotate the cylindrical lens, so I'm rotating it, you can see I can rotate the beam. Okay, now it's vertical. If I do like this, you can see even better probably that this is a plane. Can you see? Okay, in the other direction now. Okay, so if I rotate while I move, you can see it nicely. I have a trick. If I have time, I will show you my trick. My trick is use. I'll show you later. It's a nice trick though, so I want to show you. Let's go on. How large it is here in the focus? Somebody can read. Yeah. Are you sure? Okay, so then you tell me. Okay, so how large was it here? No, then it has to be the same. Because what the cylindrical lens does, it squeezes in one direction, but the other one is left untouched. So the height of the beam, it's the same. Because it doesn't do anything in one of the two directions. So now let's look at the propagation. What do you think is the thickness here? It's 0.7. Do you want to check? Want to come and check? So you have to say that it's 7, huh? It's 7.
It is 0.7.
Yeah, it's 7. Otherwise, physics doesn't work. This is a 10x objective. It will magnify 10 times, and it has a 0.28 numerical aperture. Do you think this is a large number or not? It's not. It's not. A good 10x is 0.4 usually. At least 0.3, come on, this is 0.28. Why? Well, this objective has the pro, it has a good point of being long working distance. So the focal length, it's very long, so this gives me the opportunity to mount in a three-dimensional manner my sample. So I have space. I don't need to stay here very close to the objective. I can have something that is very big. If my sample is 1 centimeter, I need to be able to move it around, for example. So I want to have room. If I was using a very high NA objective, I would have a better resolution, but good resolution is not everything. Because maybe you want to see a large field of view, which is usually what I want to do. Larger field of view. Anyway, so what we will do today, I told you that the objective has many lenses inside. Why? Exactly. So all those lenses are needed, okay, to have the right magnification, to collect as much light as possible, and to correct aberrations. In particular, chromatic aberrations. So this is a plan apo objective. Apo stands for apochromatic. It means that it's corrected for a broad range of wavelengths. Still, if after this I put a lens that is not corrected chromatically, I mean, this is useless, right? So this one is not a single lens, it's not a thin lens, it's not a single one, it is a triplet. It's probably at least a triplet, meaning that it's at least 2 or 3 lenses put all together, so that chromatic aberrations are corrected. Okay? So we will have to put this, the tube lens, after, okay? And then the camera. This objective we will put at the focal point from the plane. Okay? Then after this, which we can imagine it's just a single lens, what happens to the light? I told you already what is going on after the objective. It's collimated. Okay? So where should I put this lens? Does it really matter? And the factory who makes this tool, makes this, tells you, because otherwise, well, you could experimentally find it, but it's easier to check online. So, and I can tell you that the right range is from 7 to 17 centimeters, and what you will see is, as an effect, you will start cutting some of the frequencies of your light, and you will have an effect of vignetting. Okay, so there is a mirror mounted inside here. Okay, now I don't care, I'm not going to attach it. So do you remember what I asked you today? So what I told you today? So if we have a beam that hits a mirror, okay, so that's it, fine. So what happens if I rotate the mirror now? This is a lens of 50 millimeters focal length, so over there it's really divergent. So my question is, what happens if I rotate the mirror now with the lens in front of it? Who knows the answer? Yeah, please? No, that's not what I wanted to hear. Okay, this rotation, when you go to when you use a lens in front, will become, go closer please to my head, yeah, perfect, and now start moving very quickly, okay, quicker, means that if I rotate this mirror at the focal plane of my objective, I will be able to rigidly translate the light sheet. So this is why I want to have these 2 mirrors and these 2 lenses, to have a degree of freedom to position with a micrometric precision my light sheet, okay? Because we said we have to position it so that it matches the focal plane of the detection objective. Let's see what happens. I will do the drawing again. We don't need the first mirror anymore. So here we have a lens. Here we have our objective. So a rotation here makes a translation there. And at the focal plane, we will have a rotation. So I will be able to rotate the light sheet. Okay? So that if the light sheet is tilted, if it is at an angle, I can compensate for that by rotating the mirror. And I can do that both for the horizontal plane and the vertical plane.
One of the lenses we are going to, when you are rotating,
Yes.
going to translate. those lenses, are they the same? Are they of the same focal length?
This one, they will be the same focal length, okay?
Is the second one going to cancel the transition of the first one?
No. If actually you need both, otherwise it would not work. Yes.
And then this transition will be different on this lens.
Yes. So what does this lens do? The angular displacement that you have here, the rotation here, will be is the same at this lens. Okay. Any other question? So this system is collimated in one direction, but in the other one it's not. Okay, it's focusing here. We have to remember this. Next time I hope that we will have some good image, not just beams. All right. See you tomorrow. Have a nice night.
Supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Good morning, all. It's good to be together again. Today we are starting the 4th day of our presentations of our summer school, and we are glad that we have been able to continue being part of this. We have learned a lot, and I believe even today we shall still be able to receive quite a lot from our speakers who are lined up in the program today. I also want to welcome the online participants who have joined with us, quite a number of you. I believe also even today you are going to receive, because we have rich lectures that are coming. This morning we are honored to have Professor Geert Roix, who is going to speak to us on optics and quantum information. And I just want to give a brief introduction about Professor Roix. Professor Roix is the current president of Optica, that is this year 2024. And he is also the director emeritus at the Max Planck Institute for the Science of Light in Erlangen, Germany. I think it's important for me to mention that Professor Roix is the founding director of the Max Planck Institute for the Science of Light in Erlangen. And when I was doing my PhD, actually under him, that was the time Max Planck Institute for the Science of Light was being established. And it is actually a rigorous process to have a Max Planck Institute established. And once that happens, and it has to be reviewed by eminent international scientists, some of whom visited the Institute when I was there. But after the first 5 years, the progress of the Institute has to be reviewed so that it is affirmed. And that was done. And we got the Max Planck Institute for the Science of Light. I also want to mention that some of the areas where Professor Roix has been involved in research, his contributions range through a number of areas that includes quantum beats, photoelectron angular distribution in multiphoton ionization, reduction of quantum noise, entangled light beams and solitons in optical fibers, quantum communication protocols, focusing light beams and nanophotonics. He has done a pioneering work in the study of the focus of light and the detection of the electric field distribution in the focal region of highly focused laser beams, especially laser beams that are, have the type of polarization, radial and azimuthal polarization. He has done quite a pioneering work in that area. This morning, I would like us to welcome Professor Geert Roix. Indeed, his resume is rich. In fact, when you want to get quite a lot about him, get to the Optica website. There is a rich resume there that is for Professor Geert Roix. If I was to talk about him here, I will take the next few minutes, 10 or more minutes about the work that he has done. I would like you to give a clap to Professor Geert Roix as he comes to speak to us. And this evening, as our organizers have mentioned to us, we are going to have a dinner. We are going to have more of our speakers. They are going to tell us some of the important tips that if we follow, we are going to become successful in research, or what enabled them to become successful in the work they have done. And among them tonight will be Professor Geert Roix. So you are most welcome for tonight, even now as we settle and listen to his lecture. Welcome.
No. Okay. So let me try where should I stand? Better up, okay. So, habari. Nime furahi kuwa hapa. I'm very happy to be here. And so I don't know Kiswahili, but a lady from Kenya told this to Mojde, and Mojde told it to me. Thank you, Mojde. Okay, so first I want to make a remark to Geoffrey. So his kind words. But I wanted to emphasize one thing. So he said I was founding director of this institute, but I can tell you, you cannot do this single-handedly. I mean, if you want to establish an institute, you have to show that good research is done and everything. And I by myself, I could not have done it. So I owe, of course, to all the people who helped and worked and produced the research results. And so in the end, it was a success of all of us. And Geoffrey was part of it. Thank you, Geoffrey. So today in my lecture, I want to excuse myself that you have been waiting almost for an hour, not quite. But we had some problems. My file didn't transfer, and then I wanted to hook on my computer, and then the HDMI did not want to talk to my computer, and anyway. So when I was thinking about what to talk about today, I remembered that I know a number of people in classical optics who tell me, this field quantization, I'm not very familiar with this. This is a bit strange. When I look in books, people say now we make a transition from electric field to field operators which don't commute, so this comes out of nowhere, and so I'm not very easy with this. So then I thought, this is a bit sad, maybe one can do something. And then I understood, and when you look in the literature, you find that people have actually drawn analogies. And one analogy to like field quantization early on is something that people called wavization. And this refers to all kinds of cases in physics where you go from a non-wave theory to a wave theory. And one such example you are all familiar with very well is the transition from ray optics to wave optics. So that is one example of wavization. So in the first longer part of my lecture, I want to tell you about this. So basically it is repeating what Solania has done yesterday, and so you will recognize, but I will tell it in the frame of this wavization. And so the procedure maybe will be a bit unusual for you, but it's exactly the same diffraction and classical optics that we are describing, but the formulas we introduce to go from ray optics to wave optics can then be followed when you ask the question, how should I properly describe the excitation of the field when I go into this regime where quantum effects are important, where you need to do field quantization. So I noticed that I tried to go to fairly big font, but the resolution of the screen is not so I hope you can read. So this is the outline. So the first part is about field quantization. This is the main part, and this is, I think, what my message is supposed to be. And then I have a few other topics where I more briefly scan some information. So we start with field quantization, and when I started to think about this and talk to people, say, this field quantization is not introduced in a nice way. People have too many people have problems, and someone said, did you look in the book by Bill Louisel? He describes this. This is probably the book that describes this best. So he basically says that field operators, quadratures have to go to operators, and so Q and P, which are two quadratures of the field, like the sine and the cosine part of the electric field, they don't commute. So Q times P is not equal to P times Q. And he says the justification for the quantum postulate is the remarkable agreement between theory and experiment. It's possibly the most profound and fundamental postulate in the theory. So he clearly says that it's a bit unusual to have this postulate, but it's justified after you develop the whole theory, you apply it to experiment, and because everything goes very well, it's a justification for the initial postulate. And then I thought, this is a bit backwards, and we'll do it more straightforwardly, starting with the experiments in the first place. So, but now, in order to warm up, we look at diffraction in the language of wavization. So when you are in classical optics, ray optics, then there is Fermat's principle who tells you which path a ray takes. So if you have initial point A and you want to know which path would the light take to go to point B, then it would be a straight line in free space. And if you have interfaces between media with different refractive index, you will get refraction. And so the ray at each point is defined by the position where it starts and its direction. So direction is basically an angle. So the direction is given by a unit vector p. This is the direction of the ray, and so you can have several points. The rays start in different direction, and then you can proceed, and you have shadows and whatnot. Now, if you want to put this in more mathematics, then what you do is you take the path integral, and in order to account properly for refractive index, this refractive index is incorporated in this P, but I will show this in a minute. I was a bit ahead of myself. So in free space, the path integral would be the path element ds multiplied with P. That makes sure the ds is exactly in the direction of the ray through this vector product. And then you integrate this, and this would give you a straight line if P is always, if the modulus of P is always 1. But this will only be true in free space. So in free space, the condition is that for P to be have a modulus of 1, that Px squared plus Py squared plus Pz squared is equal to 1. Now, if you have a varying refractive index, you will have a P which varies locally depending on what the refractive index is at this point. So the 1 is then replaced by n squared, and then you can do ray tracing through with this path integral, and you say Fermat's principle minimizes the path, then you get the ray how it is propagating. So this is how it might look like. I just have like 2 points, and these are all parallel beams, parallel rays. And now we have the position where the ray starts, and you have the angle. And if you, in most cases in optics, we work in the paraxial regime, which makes things a little bit more easy because everything moves more or less from left to right. So in this paraxial regime, so these are the P, the P vectors that describe the direction of the ray. So this angle is now given because the length of P is 1. So by the x, if this is the x direction, the x component of P. So the x component of P. Now since I wrote all these P's parallel to each other, so the PX's are all the same. And now you have x and PX describing each ray, but also the ensemble of them describing the ensemble of the whole ray family. And then you can plot this in a two-dimensional diagram, two-dimensional coordinate system, which is called maybe configuration space or phase space, more usually. And so there you plot each of these rays according to its px value and its x value. Since the px's are all the same, they have the same value, but the x's are different. So you will have such a distribution. So in general, you probably have many more points, but I didn't want to show so many. So now you do experiment and you find, if my initial rays, if the range of x's where they start, if I reduce this more and more, so if you just look at the projection of this rows distribution, this should be the distribution of the many points I consider. So if I make this smaller and smaller, the experiment tells me, oh, then the px's cannot be all the same value anymore, they will scatter. So basically this is what Silvania was talking about yesterday. As you make the slit smaller, the K vector spectrum grows larger and larger. You have many more angles under which the rays are emitted. And so when you have something like this, this is nothing that you can describe with ray optics. So such a situation, which means that there is a lower bound for the area in phase space. If you make one dimension small, the other becomes larger. The product of the two is an area in this phase space. And that is clearly a sign that these quantities are somehow related by Fourier transformation, because in Fourier transformation in mathematics, this is exactly what you do. If in the initial space you go to a smaller and smaller interval, then the smaller, more narrow distribution, then in Fourier space it becomes wider and wider. So thus such experiment tells you, okay, there is some Fourier relation. And this is typical for wave phenomena, any wave phenomena in physics. Then if two variables like this x and px are related like this, then one calls this conjugate variables. So conjugate variables are always related by Fourier transformation. So instead of looking at individual rays, we now look at distributions in phase space and how this distribution develops. So it's clear from the experiment that there is this minimum area in phase space. And so we are, instead of talking about dynamics of rays, we talk about dynamics of distributions. Now there is something like marginal distributions. I think I have it here, yeah. So if suppose this is the distribution describing your system in phase space, telling you at which axis you have which ray starting, then this distribution is typically called Wigner distribution, so it's a phase-space distribution function. And you can project this phase-space distribution function on the x-axis by integrating over px. Then you will get the probability distribution of x. So what is the probability, or how many rays are starting at a particular x? And since this is a projection onto the margin, these are also called the marginal distribution. This is called a marginal distribution. But of course, you can also integrate over x and project on the p-axis. This would be this integral here. Then you would get the marginal distribution for the p-axis, and that would be the probability distribution for the axis. And now we have this Fourier transformation relation. And but suppose we don't know anything, so as usual in physics, then we try. We say, okay, there has to be a Fourier transformation relation. Maybe is it this are it these marginal distributions which are related by Fourier transformation. So we can try. Oh, I forgot. I had pictures of these marginal distributions. I didn't. So if you project on x-axis, you get a distribution which is a proper nice probability distribution, and if you project on the p-axis, you get this curve. So now the question is are this p of x and p of px, are they related by Fourier transformation? So one thing one should say in Fourier transformation, you have this factor e to the exponential of I times the product of the two conjugate variables. And of course, one has to have the dimension of 1 over the dimension of the other one, so that the product is dimensionless. Otherwise, the argument of the exponential has to be dimensionless. And x has a position, and our px was dimensionless because it was just the projection, the component of the unit vector p, or a dimensionless vector p. So the conjugate variable to x must be slightly different. It should be proportional to this px, but you have to fix the dimension. And since the dimension that is missing is length, when you go to waves, the typical dimension that enters is the wavelength. Now, if you have more time, you can actually do the experiment and look at the actual size of this lower bound that you find experimentally when you look at the fraction, and then it will come out that it is wavelengths. I'll just skip this part here. So we just put it down here, and we multiply the components of p with 2 pi divided by lambda, and we get the wave, the component of the wave vector. So now instead of talking about p probability of px, we now talk about probability of k. Now, and since the k space is like the Fourier space to x space, we call this tilde to indicate that this is a function in the Fourier transform space. It's not maybe necessary, but often it's done like this. So now the question is, can it be that the two functions, the two distributions, which are connected by Fourier transform, are these p of x and p of k? And somehow I must have skipped something. If you have such a Fourier transform expression, so if you take the px, the x appears in this on the right hand side only in the argument of the exponential. So if you want to write, there's a flip chart. Maybe I do it in words only. I'm sorry. I thought I had a slide. So when you write k times p of x. I can take this here. Yeah. So if I write down k times p of x, I can also write this as minus I d dx times p of x, and I use this p in this Fourier transform relation, and then the d dx operates only on this single x which is in there, and it takes down ik, and so this gives you just k times p of x. So the conjugate variable is also related to the differentiation with respect to the other conjugate variable, as you can see here. So x and k are the conjugate variables, and k is related to d dx. And likewise, you could also do this the other way around, that k is related to d dk if you want. Okay, so now we do a test. Now we say, let's calculate the mean value of k. So what you do is you take k and you take a probability distribution with respect to x, and in order to get the mean value you will integrate over the distribution over x. And sorry, I changed this yesterday. This should be a dk here. I forgot to. This is wrong here. This integral should be dk p of k. And then when you do this, this is fairly straightforward because the x derivative operates only here. And then you have the x integral. So the x integral basically is only the integral over the exponential, and which gives you a delta function. So in the end, because of this delta of 0, the whole thing is 0. So the average value, no matter what the distribution is, would always be 0. So obviously this does not work. So how else could it be? So another possibility is that, and in a way we are not so surprised as optics people because intensity is electric field squared. So if the probability, if we write this as the complex squared of a function psi of x, such that psi of x times psi star of x is the probability, and maybe the psi of x are Fourier related. And in a way you know this because in normal wave optics, when you do the calculations, it's the electric fields which are Fourier related and not the intensities. So what basically here it comes out by trial and error. So the intensities you see will not work. But if you do it for this psi of x, a very similar calculation here, only to get the probability for k, you operate this minus I d dx on this psi of x. What happened? Hello? Maybe if I we have people in, now it's back. We have people in Zoom, so me trying to speak up loud will not help for the people who are participating in Zoom. So, so here, this derivative with respect to x brings the k out, and now but you need a probability to get the average, you need to have an overall in probability, so you have to multiply by the psi star, and then you integrate over x, and if you do this straightforwardly, you indeed get the mean value of k. So apparently this is what it is. You have some functions describing the wave. This function multiplied with its complex conjugate give you the probability, and the probabilities are these marginal distributions. So this is how it works. So we have Fermat's principle, where this is how we started. We have this relation, how the so this is now more general. This is not only in paraxial regime with all three components, and if we have these distributions, this phase-space distribution function leads to marginal functions which are related to the complex squared of the complex squared of these wave functions, which then lead to the marginal probability distributions. And so in order to turn this equation here into a differential equation, we have to replace px by the derivatives with respect to x, and then this factor that fixes the dimension, and the same for y and z. And if we do this, we get this differential equation, or if we rewrite it. So I took all these lambda and 2 pi's all on this side here. If we rewrite it a little bit, we get the Helmholtz equation. So this, I'm sorry, maybe it took a bit long, but I wanted to show you that at the beginning in optics, when you realize there's more than only ray optics, this is a way to go to wave optics by this procedure that people in the literature called wavization. And so this phase-space distribution function plays an important role here. And so this I would like to you to keep in mind, because we will apply the same procedure now or a bit later to the quantization of the field. And this way we don't do it by just postulating suddenly some complex numbers are now operators which don't commute, which is a bit surprising at first. Instead, we go through a few more steps and apply this wavization procedure that we know and now appreciate from classical optics, and apply it to the to this other scheme. So one thing we have not discussed yet is how this phase-space distribution function is related to these marginal probability distributions, or these wave functions that make up these probability distributions. And the original paper by Wigner, this is why this is called Wigner function with a W, shows that what you need to do, basically, the phase-space distribution function is you might, loosely speaking, you might say it's a Fourier transformation of a convolution of this psi function with its complex conjugate. So this is a way you might describe this in words. Let's now suppose, let's do an example. And suppose we have a simple polynomial, psi of x, psi 1 of x is a simple polynomial. 1 refers to the fact that here we have only one 0. So it's a polynomial, but then multiplied by a Gaussian so that it doesn't grow to infinity. Which is basically something like the TM01 mode of a laser, where you have these two lobes, which are 180 degree out of phase, and this is the different sign here when you write down psi and not the, if you go to psi, the more familiar distribution for the TM01. So I don't want to take you through this in detail, but it's fairly straightforward. If you want to do this for yourself, start with this, plug in this psi function, and do the math. And what comes out is a distribution, a phase-space distribution, a Wigner function that looks like this. You see that this Wigner phase-space distribution function can have negative values. We will come back to that. So here it comes out of this calculation, but the psi you start with also has negative values, so maybe it's not so surprising. And it is rotationally symmetric in phase space, which is an important property we will emphasize on the next slide. This is this is the Wigner function of one of the possible patterns in a laser. So these laser modes, we call them the eigenmodes of the laser, and they have a particular property, and that is they are invariant under propagation. So a TM00, when it propagates, it says TM00. Now, as we know, propagation in optics is related to Fourier transformation, and if the distribution doesn't change under propagation, it must not change under Fourier transformation. So the laser modes are particular functions which are invariant under Fourier transformation, or under propagation, you might say. And the marginal distribution along x is, you might say, in a diffraction experiment, is the intensity distribution in the slit, and the marginal distribution along the k direction is, I think here it's p, so p or k. Sometimes it's intermittent here, I'm sorry. So the marginal distribution, the probability distribution of the k's tells you the probability to have certain k vectors in the near field in the plane of a slit. But you could also go far away, because then the k vector spectrum turns into a intensity spectrum as a function of position, which gives you this k vector spectrum. So the distribution has to be the same, no matter which marginal distribution you take. So this was the TM01, this is TM00, and these are the functions that you have to enter in to calculate the Wigner function for these higher laser modes. And they all have this rotational structure. And the effect that when you take the modular square of, let's say, the TM01, the effect that you have a 0 in the center means, because you also have positive, you are integrating non-zero values of the function, this means that the Wigner function cannot always only have positive values, because in order to have this to go to 0, you somehow have to, when you integrate in this perpendicular to the, what is it here, the p direction, you have to compensate for these positive values by some negative values to make it possible that the integral will be 0. So this is how they look like. And you might already wonder if these are very special functions or special fields, these laser modes, which have certain special properties, as we discussed here. Maybe they also play a role when you go to field quantization. And exactly the same functions are, these are the Wigner functions of the photon number states or Fock states in the end. So mathematically it's exactly the same, because the conditions are very similar, the procedure is very similar, so you see many similarities. Only here we are talking in optics, we are talking about a wave phenomenon in normal lab space, and when we later go to field quantization, we are in a very abstract space. This is not like x and y of in like the position in the lab. It's a more abstract Hilbert space spanned by the quadratures of the field, but we're coming to that. Another example is if you have two-slit interference, you know that the marginal distribution on the slit has two humps, so it could be two squares, or it could also be two more like Gaussians or whatever. But the individual shape does not matter so much as long as you have two distinct humps. What you will get is the double slit interference in the far field, which shows up in the spectrum of the k values on the k vector spectrum. So if you so the corresponding Wigner function looks like this: two positive humps. So red is, I think I meant red to be positive here. Two positive humps, and then there is, it looks like interference pattern, like an oscillating surface in between. So these are basically some people call it interference in phase space. So the blue is negative going, red is positive going, and so on. So it looks such a pattern. Now, if you take the marginal distribution in the x direction, then positive, negative gives you close to 0. But these big red humps, they give you positive signals. So this gives you the two bimodal distribution of the intensity in the near field. And when you instead project this whole Wigner function onto the P or K direction, then you will find that you have in the center only yellow, only positive, 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 so this is the biggest point. And then you have here positive, some negative, some positive, so this can actually go to 0, and it does. Sorry, this should be lined up, the maximum of the blue should be lined up with this 0. I now see that I should have squeezed this a bit more. Then this second minimum would be associated with this one. It's a bit skewed here. And the interesting thing is, if you don't go to the far field, to the Fraunhofer diffraction, if you go somewhere in between, as you heard yesterday, this is called Fresnel diffraction. And here, what you need to do in order to get this particular Fresnel diffraction pattern, what you can do is a projection to get a marginal distribution along one of these tilted lines. And mathematically, this is actually the fractional Fourier transform. And so all these procedures, so to treat diffraction in terms of phase-space distribution functions is not the most common thing, but people have done this. In one of the first papers you find on this is by Bastians a long time ago now. But it gives a certain way of looking at the problem, which can be quite interesting, and so some people do it this way. So the summary of this first part is that we start out with some classical phase space description. Remember, these were these individual points, x and p of x, which were still raised. They could all be parallel, and so the area in phase space at this point could actually be 0. But then you do experiments, you find that no, the area cannot be 0. There's a lower bound for the occupied volume in phase space, which hints at a Fourier relationship, and the experiments also show you typical interference patterns, which indicate there is some interference going on. And in normal diffraction optics, we can see these interference patterns with our bare eye. Of course, when we go to field quantization, then we cannot see these things with our bare eye, and so we may not see an interference pattern, but we will see some results which seem to indicate that the volume has a lower bound, or that there's a Fourier relationship, and that will then be the hint that we have to apply this wavization. And in the end, you will have non-commuting conjugate variables. So if you have as conjugate variables these x and k that span, or x and p that span phase space, then these variables are non-commuting. And maybe one easy way to see this is to say that the k corresponds to ddx, applied to the distribution function, of course. And if you take like x times ddx times psi of x, this is different from ddx times x times psi of x. So in analysis, it's clear that if you have differential operators, you cannot commute them. And this is basically ultimately also the reason why the conjugate variables in such a wave theory don't commute. In classical optics, in classical wave optics, one is typically not talking about non-commuting objects, because it's so obvious that x and ddx cannot commute. So it's not emphasized there, but it's there the same way as it is in no different way than it is later in the quantum description. And so this works not only for optics, it works for all kinds of systems. Now I have one slide. If you are interested in a unified approach to different kinds of wave phenomena like water waves, light waves, sound waves, matter waves, there is a way to look at them jointly, because basically what you need in order to come up with the very different wave equations that you can have for these different wave phenomena, what you need to know is the dispersion relation, the relation between P and K, which is this relation here, and then this you get these are the dispersion relations, and from this you now from this is not the dispersion relation, you have to integrate with respect to K, and then you get the dispersion relation, then you have a relation between K and omega in any of these different physical situations, different types of scenarios, and then you can replace the K's by ddx, and then you get the Schrödinger equation. So I just wanted to emphasize that this is somewhat related, and I think it's kind of nice that you can find this common approach to all these different scenarios. And one last comment is that such phase-based distribution models are used in quite a number of fields. Depending on which field you're in, they have different names. So, for example, so in quantum physics it's called the Wigner function, and in so if the conjugate variables are space or angle versus momentum, there's also sometimes you find it's named after Moyal. These are also papers from 1940s. Oh, here it is, 49. But conjugate variables you also have in the time domain. If your time, you Fourier transform, you go to frequency space. And this was very important in radar technology. There they're called the ambiguity function. In electrical engineering, it's called the Woodward's ambiguity function. And sometimes you find it also under the name Will function. And so this is just to tell you that although it's not so common, and when I studied physics, I did not hear much about this in my undergraduate classes, but depending on which field you are in and which papers you read, people have been using this phase space because it was helpful. I think it was important, especially in this radar technology, which went through some quick development, and it simplified some of the procedures. Okay. So now, finally, we go to field quantization, so normally when you ask the question, how do fields behave, you probably start with Maxwell equation. What we have done, starting with from paraxial optics and Fermat's principle, this is one step before Maxwell's equation. Maxwell's equation already many things entered. So once you have Maxwell's equation, with the important term that Maxwell added, which made it consistent to the other laws that were already known before, then you find that you can derive a wave equation. You can be inside a resonator, or you can have a traveling mode. And now the electric field is a function of position and time. So in many cases you can separate variables, especially if you're in an optical resonator. so that the electric field is a product of two functions, one function of R and the other one of T. We call it U and Q. U we call the mode function because it gives the spatial shape of the mode. And we normalize, of course, when you, this is somewhat artificial. Some numbers you might put into U, or you decide not to put it into U, you put it into Q. So you have to make a decision. And the decision here is that the integral over U squared, the volume integral multiplied with the permittivity, which fixes the dimension here, that this volume is set to 1. So this is a normalizing condition for this one. But this is a bit arbitrary, but it has no effect on the, you can do it also in different ways, so it does no effect on the result ultimately. So when you do this, you know that epsilon 0 times E squared is a energy density. So if you multiply it by volume, it will give you energy. But since we defined U squared here such that this is 1, when you square E, you have Q squared. So Q squared has the dimension of energy, right? So if you take epsilon 0 E squared, integrate it over volume, you get one term which is dimensionless, and then you get Q squared, and this has to have a dimension of energy. And then you can separate variables. You can write this wave equation in a spatially varying part and a temporal part. And here you recognize Helmholtz equation, which we derived before through this wavization from ray optics. But the other one, and this is now the important one for what is to come, this is, sorry, this is wrong. This is the Helmholtz equation, of course. I did this morning. I was not focusing enough. So Helmholtz equation is not this one, but this one, of course. And the more important one that we focus on now is the remaining equation, which tells you, which is a differential equation for this Q. And basically Q, since this here is normalized, Q is proportional to the field quadrature. So is the electric field, the oscillating electric field. You have always a cosine and a sine part, or the Q and its derivatives. This is kind of like two-dimensional. And so this equation is about the excitation of the mode. I mean, the field that's in there. And in classical wave optics, the Q is just some complex number in general, or a real number, depending on how you define it. Of course, this looks like a harmonic oscillator. Then we could say, we can look in the quantum physics book how you quantize the harmonic oscillator. But you can also say, well, I don't look into these books. We want to do it using this wavization, the procedure for which we have intuition if we come from optics. So the excitation of a mode will somehow look like this. The Q can be written as as usual as real numbers, or you can also have the exponential complex description. So we use this real description. So Q of t would be an amplitude times cosine of omega t, omega given by C and K here, these quantities, the frequency, plus sine of omega t. So for t equals 0, this is 0. So the coefficient in front of this here will be related to the time derivative of q and its value at 0. So you have here q of 0 and q dot of 0, they determine the whole evolution. Now you can turn this into an equation which for just these two amplitudes, q of 0 and q dot of 0. And why is this cut off a bit? I noticed. It's only like 5 centimeters. I hope nothing important is on this side. Now you could, again, these are typically these two quantities, they define the state. So you can plot it in 2D. So if you plot q dot of 0 versus q0, then for one particular choice of parameters, this will give you a dot here. So there will be amplitude and phase, you could say, or there will be two quadrature values, coefficients of the cosine part of the wave or the sine part of the wave, or we could call it, as we did, q of 0 and q dot of 0 divided by omega. So now we do experiment, like we have done in the case of diffraction. And so the simplest experiment we can do is to put the light field onto a direct detector. Then you will see some noise, and this will tell you how noisy the amplitude quadrature is. So if this is noisy, it could still be that the proper distribution in phase space is not a point, but maybe along a line. So it could still have a zero area. But you can also do another experiment. You can try to be sensitive not only to amplitude, but also to phase. And the way to do this in optics, so this is not so more straightforward, is to measure intensity or amplitude, because this is just a simple measurement like this here. If you want to measure the phase, you have to somehow relate the phase to something else. So basically what you need is a reference wave, which is often called local oscillator. This comes from radio technology in the 1920s and 30s, because in order to look for if you have frequency modulation in the radio wave, you have to demodulate, and for this you need a reference wave. And this was created in the radio receiver locally in the living room where the receiver stood. And this is why this reference wave is now in all other cases outside radio technology. It's also called local oscillator, just in case you wonder about the name. So basically it's a laser beam with as fixed a phase as possible. And then you interfere it with your light field under study, and you have two output ports where the two interfere. There are phase relation that the beam splitter one has to pay attention to. And then if you then measure the intensity in the two output ports and take the derivative, the difference of these two signals, then you get information about the phase. So let's do this. And so I will now tell you which kind of numbers I use to explain the light field that is coming from the source, which is under study, and the light field, which is the phase reference. So watch out. So we have, there is a Q1 describes the field here, Q1 and the Q.1 accordingly, of course. And so the Q2, I see, I'm sorry, I switched. So the Q I showed you before was all real, but now I think of the Q as a complex number, so Q is a modulus of Q times e to the I times the phase. So this is like this complex amplitude phase description. This is why you see complex conjugates here. So this Q1 describes the unknown field, Q2 describes the local oscillator, and then on the other side of the beam splitter you mix the two, and the way you mix them, you have to be careful about the phase shift at the beam splitter. So this, you can account for this by this change of sign. So basically on the output you have a symmetric and anti-symmetric superposition of Q1 and Q2 properly normalized. And then the intensity is the modulus square of the Q1 prime and Q2 prime at the two outputs. And when you do this, you get these numbers. And when you take the difference of the two, this disappears, these survive here. And so basically what you have is you get 2 times the real part of Q1 and Q2 star. So these cancel because of the minus sign if you take the difference. And so these add up, and basically it's Q1, Q2 star, plus Q1 star, Q2, and this is the real part of Q1, Q2 star. And so if Q1, if this is 0, then of course the difference has to be 0. So now we do the experiment, I hope. Come on. So suppose at first we have no light on both output ports. And then the I2 minus I1, I have to tell you it's not really constant, because the detectors here have amplifiers and there's some electronic noise in the amplifier. But if you build them carefully enough and well enough, you can keep this amplifier, this electronic noise low enough. And this is one of the tricks in experimental quantum optics, to have detectors that have such qualities. And but then Q1 is 0 and Q2 is 0. Now suppose you switch on the local oscillator, so the Q2 is now different from 0, but still there is no light coming in on this side. And you would expect just to see electronic noise, because the Q1 equals 0 would take the product to 0. But what you see is that there is actually noise. And as you increase the intensity, as you increase Q, modulus of Q2, then this increases. So there's noise in the light. There must be noise also in Q1. So if we say Q1 is equal to 0, this is maybe loosely speaking, it's maybe only on average is 0. And to explain this behavior here, it must mean that Q1 maybe can be on average 0, but there must be some oscillation around 0 so that the variance is not 0. And that gives you a signal and output side, which is on average 0, but if you look at the timeline, you have a large noise, so the variance is can be larger and larger the stronger the local oscillator phase is. Now, the stronger the local oscillator intensity is. There's another experiment that has been done in at Lake Constance a little more than 20 years ago. This was a pulsed laser, a down converter. So basically, this was a way to create a single photon. So at this point, we have not quantized the light field, but we can take a black box from a quantum optics lab and take it to a classical optics lab, and we study whatever light comes what you do, what you find here is you actually, so this is actually the measurement to the sketchy scheme that I showed you on the previous one. So we can actually do measurements and we can determine the variance, and these are experiments that one can do to show that there is something beyond the Maxwell's equation where the amplitudes are just, the excitations are just complex numbers. The way we think about this in phase space is that because we see this same picture independent of the phase of the local oscillator, so the phase space distribution function describing the excitation in the field mode under study cannot be a single point, which would be the classical regime, but it has to be a blob which is extended in all directions, Q and Q dot and all other directions, because when we take a local oscillator and change the phase and look at the intensity at the output of this interference between local oscillator and the signal, which is called homodyning, then by changing the phase we do marginal distributions on different angles. So we change the angle of the axis onto which we do the projection, where we measure the marginal distribution. And since this is rotationally symmetric, the same everywhere, it must be a rotationally symmetric phase-space distribution function. You can also do simultaneous phase and amplitude measurement. For this you have to split the light field under study in two and measure amplitude in one and phase in the other, or the one quadrature in one and the orthogonal quadrature in the other. But the thing is that this comes with a noise penalty, so you can do this too, and in some cases it makes sense to do such measurements. It has also some advantages, but the downside is that on this beam splitter you enter some noise, because the light field can never be completely at zero. So this you will see, but this is anticipating what we will find. So instead of having a point here, we have a finite distribution. If we squeeze, if we have a light field which has less amplitude variance, which is possible, but then in the experiment we will find that then the variance in the phase direction is larger, so that we have this signature that there is a lower bound for the area and phase space, which is a hint that there is a Fourier relationship like the one we discussed in diffraction. I'm sorry, the time is running. Maybe I go through this quickly. So basically, we can now look at some numbers and fix everything, but you can see the similarity. We start out with points in phase space, and then we do experiments. We see these are extended. This has to do with Fourier transformation. So basically, in these two conjugate variables, one is the derivative corresponds to the derivative with respect to the other. So instead of having x and k, you have x and d dx. And this is the same here. The only difference, the big difference, is that here we have these, the q and the q dot here. These are quadratures of the field, and they are not, or the q is a quadrature of the field, and it's not the x position in lab, the normal coordinate in our normal lab coordinate system. So this is why it's maybe a bit, you have to get used to a bit more. So it's you're talking about such experiments in some more abstract space, not in the position space in the lab. But otherwise, it's very similar. So I think I can skip this. This is just to say that you can look at. So you have the if you have x, the conjugate variable is related to the derivative with respect to x. But if you start with t or with phi or any other quantity, this works whenever you have such Fourier relationships. And then the action complement is either the momentum or the energy in the case of time. In the case of phase, it's the angular momentum. So this tells you that this whole procedure can be applied in many areas and many different physical types of conjugate variables. So what is still missing is really the relationship now between this q dot and p. It's a little bit like this factor lambda over 2 pi that we inserted quickly. And so now we can do experiments with laser, which has this shot noise, which is related to the fact that it cannot be a point in phase space. And we can look at how much power is in the noise. So this will be very small, but it's detectable. So for a helium neon laser of 1 milliwatt, if you measure in a radio frequency band of 1 megahertz, you will get a power which is a power variance which is a little bit more than 10 to minus 8 watts, which sounds very small, and it is small, but it's non-negligible. And of course, as the power goes up, this number also goes up. So then you can deduce the area in phase space and get this factor that relates Q and P. And so basically what it is, it's the, so Q dot divided by omega is related to P by adding this H bar omega divided by 2. So here we get the H bar Planck's constant basically determines the lower bound in this regime. So then it is basically straightforward. You have this relationship between Q dot of 0 and Q of 0, which we started out with. Now, if we replace the Q dot by a derivative, we have to insert distribution functions before that in order to make this make sense of this. And like in the wavization in diffraction, these will not be the marginal distributions, but it will be the underlying wave functions. And so if you do this, basically you recover the Schrödinger equation for the, you might say, for the harmonic oscillator for this particular system. But we have done this in a way without kind of borrowing too much from textbooks, but you can go stepwise, you can go through this and using your intuition as a classical optician. So I thought this was kind of nice. Okay, so then we have, you can also write this in terms of these field operators, but that's just a redefinition. This up here, so Q, DDQ, if you combine them in a particular way, you can define new operators, which also will not commute, like Q and DDQ don't commute. Then the eigenfunctions of the intensity. Intensity is so the eigenfunctions of this equation are the eigenfunctions of energy, and these are the Fock states or photon number states. And if you look formally, they are exactly the same as the laser modes, because it is the same thing. They are independent of phase in phase space. which means which corresponds to independence of propagation in the case of diffraction. So they have to be rotationally symmetric in phase space. These are functions which are invariant under Fourier transformation. So mathematically they look exactly the same. Only the variables in here are not even in the quantum domain. Sometimes people use x, but it's not the x of position, but it's x in this excitation space describing the excitation of the modes. Okay, so these field operators make life easy once you get used to them. The one is called the lowering operator, the other one the creation operator, because when they operate on one of these energy eigenfunctions, which you abbreviate just as n in this cat notation, then you lower the photon number by 1, the other one increase the photon number by 1. So this all comes out. You just have to sit down and go through a few lines, and this all follows from what we have done so far, basically from this equation. I think I skipped this. You can use. You can ask, there is some interesting aspect. The eigenfunction of A is actually the so-called coherent state, which is the state which has at the same time both a fairly well-defined amplitude and phase. So it's kind of like a circular region of uncertainty in phase space. This is the eigenfunction of A, and for reasons which is interesting to look at, there is no eigenfunction of a dagger. So there's some asymmetry here. And I think I skipped this. Here is there. So here are different types of field. Oops. Which way did I go? Here. So this is a table. I wanted the laser pointer here. So the vacuum state. This is the ground state of the excitation. It's not all the. This is not a point in phase space. It cannot be, because there is a minimum area in phase space, so it has this minimum area centered around 0. So it has vacuum uncertainty or 0-point fluctuations, or as you might call it. And this you can describe in these continuous quadrature variables. Then the wave function looks like a exponential, like a Gaussian. If you use the eigenfunctions of the energy operator, then this is the 0 photon state, but it has this Gaussian shaped distribution in phase space, so this is the wave function, and in phase space the Wigner function. This is a two-dimensional Gaussian. So this the wave function is a one-dimensional Gaussian. Do you remember the Wigner function is kind of, loosely speaking, the Fourier transform of the convolution of psi and psi star. So that gives you a two-dimensional. So you can describe the different types: vacuum state, Fock state, coherent state, thermal state, squeeze state, or cat state. Actually, the cat state, the Wigner function looks exactly like the Wigner function of the two-slit interference. So the two-slit interference Wigner function is kind of the counterpart of the quantum mechanical cat state. So this is a kind of a rich scenario, and you can look into this, and you have, if you want to describe a particular problem, you have, as usual, a choice to use you use one way of describing it or another, and sometimes, often, one of the ways you can describe it with is more efficient. let's see. I have 10 more minutes. We're still here. Good. So, importance of measurement in quantum physics. I try to do this more with pictures than with mathematics, because you have seen so many equations already. So, in the classical world, if you want to do a measurement, suppose you have a wave, like a wave in water, although it doesn't look like a wave in water, but you can imagine. Then in classical physics, what we can do is we take a camera and click on the camera, and it will take a picture, and it will look like this, very clear. Now, in the quantum world, these cameras don't work to measure the wave functions in the quantum world. In the quantum world, you have some apparatus which is built such that whatever you can observe is sensitive to the quantum properties, but it looks like any optical setup. You cannot really, just from looking at the optical table briefly, you would not be able to tell this is a quantum or a classical experiment, but when you look closer, one is able to tell. But here, you don't have a camera, but you have, of course, ways to do measurements. And so somehow you hook the whole thing up to a computer, and then you can try to visualize what you have measured on the computer. Now, what happens that in the quantum system, typically you are in a superposition of states. Superposition of states that give you a particular outcome. So, for example, the outcome, suppose you look at like an electron, and the electron has a wave function. So we know the electron from Newtonian to quantum mechanics, it's also like a wavization, very similar to what we discussed. So the electron is described by a wave function. And so suppose we want to measure the position of the electron. But since it is described by a wave function, the position is not clearly defined. It's somewhat diffuse, like any wave. Also, water waves are not. The position of the wave is not defined because you have a distribution. So when you have, the electron will be in a superposition of being in one place, in another place, or in a third place, all described by this distribution of the envelope. And now what happens in the experiment, if the detector measures space, but the object that you measure is in a superposition of different locations, positions, then in the quantum measurement, you always do a projection. You will get only one of the possible values. So basically, suppose this is position, like this was also position, then you will get just some signal at some particular position. Then you repeat the experiment identically, and next time you get another outcome, and another outcome, and so on. And eventually, what you can do is you can plot all these results at the same time, so you build up a histogram, and then you will begin to see the wave pattern. So the typical thing in quantum physics is that there is more information in the system than you can read out with a single measurement. By identically preparing the system many times and repeating the measurement, you can build up the histogram. Then this is a way to get out the distribution, which is so easily recorded in the classical world. So we have this very strange effect that by doing a single measurement on a single quantum system, you cannot recover all the information that is there. You will lose much of the information and retrieve only some. And which you retrieve, you cannot influence. So there is even like a random process involved. So some people even build random number generators using quantum measurement process. This long time ago, it was often called the collapse of the wave function, but the word collapse, like in an implosion, suggests some dynamical evolution, and there's no indication that what happens here is evolution is a function of time. This is why many people don't like this notion of the collapse of the wave function. So the fact that you reduce the wave function to just one of the possible, I mean, you lose much here, as you can see. So rather, people prefer nowadays to say projection, because this is a mathematical term, and the thing is, the faster you can look, the faster this projection happens. So I think people working in the field, they got used to this, and this is how it happens. But if you ask the question, but how can I understand this? What's behind there? I think there's no real good answer. But this is not the only case. If you ask yourself, what keeps me on the ground? Many people would say, like, gravity is clear. I mean, I understand gravity, this is normal. But when you ask what it is from a point of view of a physicist, you can describe it. You can say, well, there's a force. It depends on the product of the two masses, and it becomes smaller with 1/r² when you increase the distance between them. But when you say, what is the nature? What is the force? So if you, poke more and more and ask this question, nobody can tell you. So I think this is probably, nature behaves in the way it behaves, and we as human beings can observe nature and try to come up with models and describe this, and we can do this very well, because even without understanding, then you can ask yourself, what does it mean if I say I understand? Maybe not understanding the first principles of gravity, and not only gravity, I can take anything else. But gravity is the one thing that most people, even non-physicists, when you ask them, they say, no, gravity I understand. But it's not so well understood if you really go into the fundamentals. And but what we can do, we can predict the motion of the moon, and we can send spacecraft to long distances. We know exactly what will happen because we have all the mathematics and everything. But the underlying question, what does it mean? But this is not necessary. We just have to accept how it is, and that we have a good way of describing it. And in a way, I think it's the same with the quantum measurement process, only this is not something that we grew up with when we are kids. So superposition contains more of a superposition state contains information about two or more states, the states that seem mutually exclusive, for example, when you say an electron is in position x and x1 and x2, and x1 is not equal to x2, you might say, can it be in both places? Well, when you think it's a wave, you can probably accept. But when you have this in quantum physics and you do a measurement, then you lose. For a long time, I thought there's nothing in the real world, everyday life, which I can use to talk to non-physicists. You all are physicists, but sometimes I give talks to non-physicists. And then I thought, but there's one thing which has nothing to do with quantum, but there's one thing in our everyday life, in our or in arts or whatever, part of our everyday life, where we have a similar situation. And there it is that you have pictures and you take many details out so that two different pictures, which are mutually exclusive, appear as the same sketchy drawing. So this, probably, I think you might all know this. Here you can see a younger lady, then this is a necklace, or an older lady, then this is the, so for young ladies this is chin and necklace, and for older lady this is nose and mouth. So, and I think you can see only one. Our brain can switch. When you know you can see both of them, you can switch. This you cannot do in a quantum measurement. If you do a measurement and you had this projection, you cannot switch anymore. But this is not, I mean, this has nothing to do with quantum physics, but it's the best. Hello, hello. Can you switch me? Yeah, I'm back on, I guess. But this is the best example I can offer you from everyday life, which has this similar notation that you find in quantum measurement, that you have a breadth of information, but you're only able to recover one part. Another example is this. So you can see a vase, a black vase, or two faces. But this is, what I like better is more abstract. What I like better is such a cube, where you only draw the corners. And then this is also a superposition, because the orientation of this cube can be two different types, like this one or this one. So by leaving, so this is a transparent cube where you see only the edges. And here I left off, so if the cube were not transparent, I leave off the ones that you don't see because they're behind. So in one case, so the front facet looks to the lower left, and here the front facet looks to the upper right. So they are not the same. So this is very similar, only you don't have to, it's more abstract. So now in quantum physics you can also have several systems, and and they can be in superpositions, and then there's something called quantum entanglement. These are correlations between individual systems. So now in this kind of the cubes, I can also call everyday example from everyday life, right? Although we don't see these cubes like this as often as other things. So if I put like 4 of them in a row, chances are if you see one of the cubes in one particular way, one of the two, that the others you see the same way. This is how the brain works. So basically this example here works because our brain is making associations, and so in the quantum world, it's some aspects are a bit similar. That to the extent that you can see all 4 of them looking downward, the front facet, or the front facet going upward, then the quantum description of such a state would be all cubes in this orientation plus all cubes in this orientation. And then when you do a measurement on one of them, then you will see this one way or the other, either like this or like this. And if this were a quantum measurement, if you do the measurement and this appears in a particular way, you have a projection, and suppose you see this one, then you project on this part of the wave function, and then all the others have the same orientation no matter what. And this means that you can have Yeah, okay. So now there is 100% correlation. So conditioned on this first measurement, if I now do the same measurement on number 2, 3, or 4, I can predict with 100% certainty what the outcome is. Although if I hadn't done this first experiment onto which I conditioned, if I would measure the third one or the fourth one, I would see you would still have the superposition, either or one or the other orientation of the cube. And this is why you can think of building quantum computers, and so computers using quantum systems. So initially the idea was this would be fantastic because a quantum register can be in a superposition of many possible states. So you can do massive parallel computing, but at some point you have to measure the result, and when you do the measurement, bang, you have the projection and you lose it all. But because of this correlation that you can have, this strong correlation, or the other thing you could say, but these quantum systems, they have this uncertainty, and can you do precise calculations because of the uncertainty and different outcomes that you can have. But because you can have such very strong correlations, this then basically, in a nutshell, explains why it makes sense to think about quantum computer. I think, this is how much I'm over time. I mean, that I started late was my fault and not your fault. Let's see, maybe I'll show you this and then I skip the rest because this is nice. So if you now prepare light field in one of these eigenstates of the energy, namely the first one, the first excited state, which one calls a single photon, like the first excitation of the mode. So Philippe Grangier, Roger and Alain Aspect, they did an experiment, cited many times, where they prepared actually they had a pair, they produced a pair of photons and they conditioned on this measurement, and they knew when there was a click here, they must have had a photon here. And so they condition the measurements on the output of the beam splitter. There are two detectors. They condition this on this click here. So it means there must be a photon somewhere. And so then the outcome is that it is either this detector gives signal or this detector gives signal, saying that a single photon can only be transmitted or reflected, like here, a single photon coming in, and this is a beam splitter cube, and so either this detector clicks and this detector clicks. And you probably have heard this many times, a single photon cannot go both ways, but it can only go one way or the other. This is perfectly fine and true for this experiment, but when you do other experiments, it's not so clear anymore. For example, with a single photon, you can operate an interferometer. You have a first beam splitter, and then there are the two different passes the photon can take. Then there's another beam splitter, and they are recombined. And so now it makes, if the photon would only go on one of these passes, how could you have interference? So there, the proper explanation is the photon actually kind of splits up, and then when it's recombined, the way it is recombined depends on the relative phase of the two, the path length difference of the two passes. And how do you combine these two pictures? So after the beam splitter, you have either zero photon here and one photon here, or one photon here and zero photon there. So you have such a superposition, so 0, 1 plus 1, 0. And now when you do a measurement where you're sensitive to whether this is 1 or 0, and you measure on one output port of the beam splitter, you project onto one of these, 0, 1 or 1, 0. And so if you only have 0, 1 and you measured the 0 or the 1, then you know the other one will be 1 or 0. So this is exactly what this is here. But if you don't measure the 1, if you choose to measure some other properties, then it is different. And I wished I had thought of this myself, but I didn't. It was the experiment was done in the group of Gunnar Björk in Sweden. It was a PhD thesis of Björn Hesmo in, when was it? I can't read, 2004 maybe. There was a theory paper. It was Luis Sanchez Soto from Madrid, Gunnar Björk, and there was in the early 2000s there was a controversy. So when you have a single photon on a beam splitter, and after the beam splitter in these two modes you have either 0 photon in one, 1 photon in the other, so 0, 1 plus 1, 0. This looks like an entangled state, but some people argued, but this is only 1 photon. So in 1 photon I can only measure once, there is no correlation, so should one call this entanglement or not? So you can look in the literature, there's a heated debate. And basically, as I recall it, it's this experiment here that resolved the situation. And so this is the ICO, International Commission of Optics newsletter, 2016. So I really regretted not having had the idea myself. I would have loved to do this experiment. So when I was asked to write an article for the International Year of Light about quantum optics, I chose this. So there's a short essay there. So what they do is they produce a single photon. Here, so they have a laser, they have second harmonic generation, this pumps a nonlinear crystal, so you produce a photon pair, and so you can, like in the other experiment by Aspe, you can conditionally prepare a single photon, and so this comes in here, and the laser, before, so if this is like signal Eitler have the same frequency, this frequency is basically the same as the laser frequency. So if you have the frequency degeneracy here, and so you can choose by the angle whether you have that or not. And then they took this laser beam before second harmonic generation as a local oscillator to not measure the energy, but to measure the quadrature of this photon. So now, because it's not the energy that was measured, because if you measure the energy, the result is photon goes one way or the other. But if you measure the quadrature, that's a different story. And so basically, they could have a correlation between the two output ports. It's a bit more complicated because they had these two local oscillators that you use here. This is because it was done with polarization. This is a bit intermingled here. So this is the more simple sketch. Now you can use different phase relations. So depending on how you adjust the phase relation of this local oscillator, this will affect the measurement. So you can have no correlation, you can have positive correlation, you can have negative correlation. But if you kind of block off the single photon, you will still see some noise because the local oscillator will heterodyne the vacuum, but then there will be no correlation. The correlation, either positive or negative, is only produced by the single photon. So that was a very nice paper. This is one of the results. And okay, then the rest is just, you can use this for interferometry, or computation. I already hinted at. There were, especially for optics, there's something like boson sampling, which is a hot topic at the moment, in discrete and also in continuous Gaussian refers to continuous quadrature type variable boson sampling. And so the last bit was quantum communication, and there the fact that by doing a measurement you lose many things. This is why a unwanted eavesdropper can be detected when he or she interferes in the communication line. Then you can implement this in fiber technology, in free space, including satellite, and so there are many groups worldwide working on this. And quantum communication is also the topic of how can you kind of build a communication link, a bus between different quantum computers once they will be existing. So there are this is all topics from that part. So I'm sorry for going over time. Thank you very much.
Thank you so much, Dr. Alex. I think questions, some that you'd like to clarify, anything to do with the lecture that
to clarify where the quantum came about, was the definition of A and A dagger? Or
Say again?
like that quantum, like that you have no community?
Yeah.
The definition of an A and A dagger?
No, I think the quantum came in when you realize that these quadratures are related by Fourier transform. So it's as soon as the wave nature becomes apparent, so that you have some kind of like a wave phenomenon in this abstract space.
Yeah, but in classical is also like that. In classical is also Fourier transform.
Which is also?
In the classical one.
Yeah.
But where the
Yes. So if you ask me, for me, there's not much difference between the different wave phenomena. When you look at like the wave equation that you like Helmholtz equation, or you look at Schrödinger equation for matter waves, or the differential equation for water waves, which is yet different. You can give this to a mathematician, and the mathematician will give you solutions. You do not have to tell the mathematician, be careful, this equation is classical physics, and this equation is quantum physics. You have to be careful, maybe you have to do the calculation differently. No, he applies his mathematical formulas and finds the functions that solve this. So I think if it were not for the special property of the measurement process, which is related to what is the physical meaning of the wave function. So in quantum, the physical meaning of the wave function is that the absolute square has to do with the probability that the projection will happen. So it's related to this projection. Whereas in these other waves, like water wave, which is the simplest we can see, we know it's either the height or maybe what we don't see so easily, but if there's something floating on the water, you can see that there's also transverse motion and velocities. You can also write the equation for the velocities, and then it's very clear. These are really, this has nothing to do with probability. These are some properties of the water elements moving around. So I think it is the measurement process ultimately that makes a distinction. If it were not for that, I think matter waves would be just yet another wave phenomenon in physics as many others. Because you could ask the same question. Someone who believes in ray optics and has never done any experiments where he got into trouble with ray optics, he might question, is it really necessary to do some wave optics? This is a bit strange. I find this a bit strange. And then you can also ask the question, when is it that in your procedure, in your argument, when is it that the wave nature becomes apparent? And I think it's when you recognize that you have this minimum area and phase space, which is related to the fact that the variables are related by Fourier transformation. But we can talk more about this. I mean, different people will probably say this, answer this differently, but I think, so for me, it's the most natural situation that as long as you don't measure, you cannot even really tell the difference between a quantum wave and some other wave.
More questions?
And if you, I didn't cite so many, but I cited a few papers. If you're interested in one of them and you cannot find it, you can write to me. I can send you.
My question is on the low-cost data. When you are making the homodynamic experiment, what are the challenges you encounter?
As usual in experimental physics, you have to have components which have good enough quality, and you have to be careful enough in doing the experiment. There are many details I did not mention, of course. So, for example, classical optics is very important, and wavefronts when it comes to homodynamic, because I was just writing two arrows and they meet at the beam splitter and they combine with a plus or minus sign. But these are wavefronts. So if for some reason in one output port of the beam splitter and the other output port, the wavefront for some reason is not exactly the same as in the other, this will affect the measurement. So so there's something called the homodynamic efficiency. This depends on how well the wavefront of the signal and the wavefront of the local oscillator is matched. So this is certainly a challenge which is not so easy. You have to be aware of, and I have to. Your detector, if your detector is better has a high quantum efficiency, because otherwise you have. So if the detector is fairly lossy, this adds noise, and this may be relevant. If your signal is very high, this aspect is probably not so important, but the matching of the wavefronts, this is important no matter at which level, at which intensity level you detect. This is the first two things that come to my mind. If I can think of more, I'll tell you.
Yeah, Professor Lloyd, when you are talking about the Wigner functions, this was coming to my attention about the electric field that the functions we use to describe the electric field of the transverse modes in RAC. These functions, when you get the intensity, it gives you the band patterns of the different modes, of RAC transverse mode. So I think the Wigner functions and the electric field functions that we use to describe these modes, they almost look the same.
Yeah, it's so the electric field is related to, I called it psi. I think I called it psi because later in quantum physics you also call it psi. But when you think of you have the Wigner function and the marginal distribution, and the marginal distribution in classical optics would be the intensity. But the intensities are not related by Fourier transform, as we know. It's the electric fields. So the underlying electric field distributions are the ones that are these functions that appear in this integral. I showed you how to calculate the Wigner function from. You can also calculate it from density matrices in quantum mechanics, but for classical optics, probably more relevant. that the electric field functions. So basically, you take electric field at so it's how should I say? On the axis of phase space, there is a quadrature. These are the different possible values of the electric field. And the function psi is a distribution function of with what weight do I have one quadrature or the other quadrature. So it's these field distribution functions which you have to convolute and Fourier transform to get the Wigner function. And the power of the Wigner function is that everything is in there. Oh, I forgot one thing. Moshe, you on your first day, you explained how you can get the correlation function, intensity correlation function from Wigner function. You did this on Monday, right? So this is the beauty of this approach, because the Wigner function, like density matrices in quantum mechanics, they have the full information. So every aspect, every property of your system, you can calculate from the Wigner function. And one example is intensity correlation function, which is not so obvious, but when you, Moshe knows how to do it, he told you. So it's, the nice thing about the Wigner function is that all the information about the state, about the mode, is about the excitation is in there. And another story is about all the spatial and temporal distribution, and this is given by my solutions to the Helmholtz equation. These are these two aspects that you have. So here in this field quantization, basically you deal with how to treat the excitation of the modes, and the modes themselves are determined by Helmholtz equation, for example.
Probably the last one, Pro. These days we are talking quite a lot about quantum computing.
Mm-hmm.
And it's like there's a lot of energy that is spent towards that direction. So what are your comments about the possibility of realizing this and probably having that technology deployed in the future?
Yes. So the thing, it's a bit tricky. So the first time people started to talk about quantum computer is 40 years ago. Actually, Richard Feynman made the proposal that this would be the ultimate way to calculate efficiently some complex problems. So it's started in the last 10, 20 years maybe, that now there are some big companies got involved, many startups are involved, and I think if you can get the interest of the people, private people who have a lot of money, who wonder where to invest this, you can get quite some support. And somehow these startups, none of which has built a functioning quantum computer, they told a story which interested people enough so that they got a lot of funding. So in principle it's possible, it's clear that in principle it's possible to build a quantum computer. The thing is that I think a quantum computer will never fully replace the classical computer. This seems to be pretty clear. But there are certain tasks where a quantum computer is much more efficient. And this is related to the fact that ultimately, in order to know what the computer calculated, you have to look. That means you have to measure. So you have this projection. it's unavoidable. Even if I told you we don't know exactly what does it mean, this projection, how can we explain this, we have to get used to this, but all of the experiments that have been done in the last 100 years or so show that we have to somehow live with this. So the thing is that the efficiency of the quantum computer comes from the fact that you can have the input register in a superposition of all possible states. Like in a classical computer, you have to tell it, calculate this and this and this, and you have to put some initial values. And then you can change the initial value and can see how things change. So in a quantum computer, you can put the input register in a superposition of all these possible values, and then you run the computer once, and then the output register and the input register are entangled such that if you measure both of them, you will pick out, because of this close to 100% or principle 100% correlation, you pick out a pair that belongs to each other, like an input data which corresponds to this calculation. Before you do the measurement, all this is there, like these many different cubes, which could be differently oriented. But when you do a measurement, it reduces to one pair, and then you lost all the. So, from this argument, you might wonder, why is there a big hype about a quantum computer? If intrinsically there is parallel processing, but I cannot get it out, because if I do a measurement, I lose it all. Now the thing is, all the examples where people said, here is a quantum algorithm which will run on a quantum computer much, much more efficiently to solve a complicated problem than on a classical computer. And the most famous one is probably factorizing large numbers. So the one direction is very easy. We have very efficient algorithms how to multiply two numbers, even if they are big. We just have to go through the procedure. If alternatively we are given a big number and we are asked what are the factors, basically most algorithms basically kind of check one by one. Does this work? Does this work? Does this work? This is exponentially, takes exponentially long time, which in computer science, when the time required increases exponentially, then they say this is an unsolvable problem, because you can increase the mantissa so long that even when you start calculating now, even your grandchildren will not have gotten the result. This one can show, at least in theory, this can be solved by a quantum computer much better. And why is this? This is because ultimately there is an algorithm which was published by Peter Shaw, yeah. So there, he has this algorithm which you can calculate on the classical computer, but there's one step where the classical computer needs a long time, and this step is the following. So you have in Shor's algorithm, you need the period of a function. You need to know the period of the function. And numerically in a classical computer, how do you measure the period? You measure point by point. You calculate function values one after the other, and then you can plot the function, and then you can determine the period, maybe by Fourier transform. But this requires many steps, and if you increase the mantissa of this large number that you want to factorize, this particular step to determine the period of the function on a classical computer, this time increases exponentially with mantissa lengths. So people say, well, this is forbiddingly long. And so it's used in secure communication, this asymmetry between multiplication and factoring. And, but of course, computers, even classical computers, get better. So at some point, even though it's exponential, they can do this in maybe a day. And this is not good for security. So what people did, they doubled the mantissa. They doubled the number of digits. And then it was unsolvable immediately again. Now, why would a quantum computer be potentially be more efficient? And it's exactly because all these different function values that the classical computer has to calculate, which takes so much time, is not what you need in the algorithm. What you need is the period, and the period is only one number. So the trick is, now in the quantum computer, you can put all the initial values in the register. You put the register in the input register in a superposition of all the possible input, and then you run the algorithm that produces the function, and then you have massive parallelism. You have the output and the input are entangled, and all the information is there. The only thing you should not do is now do a measurement, because then you lose. We were talking about this. So you don't do the measurement then. Instead, you apply a quantum Fourier transform on the input-output register on the system, and the quantum Fourier transform gives you, you go to in the Fourier transform space, this is the spectrum of periods. And if this is a function that has one period, there will be one peak. So you first do the quantum Fourier transform and then do a measurement, and this measurement gives you the frequency. And this is only one frequency, then the quantum computer will work, because you get, in the projection, you get one out, and if this is the one result that is there, you will get it. And this is why you have this large speed up. But it's also the reason why, when you ask which quantum algorithms have people found where the quantum computer is where the power of the quantum computer is really usable, this is somewhat limited. And another class where quantum computers work very well is if you calculate a quantum system, like in pharmacy, you're interested in certain molecules and maybe their configuration or their ground state energy, and if you're interested in this, you will have to work in high-dimensional Hilbert space, and a quantum computer also works in high-dimensional Hilbert space. So this is kind of like adopted. This is why Richard Feynman initially thought such a quantum computer might be good. And then when you're interested in the ground state energy or the configuration, this is a little bit like one number or one property. So this is where also people hope that quantum computers can be very helpful. But there are many tasks where they will not be better than classical computers, so the classical computers will not disappear.
Okay, thank you so much. Let's give a clap to Mr. Lake.
Thank you.
We are going to have a tea break now, but just one announcement to make. After the lecture by Professor Peleila, we are going to have a photo session, which is going to happen here on stage. This place looks good. I think we need to have a photo from here. Tonight, we are also going to give a prize to the best posters that were presented yesterday. So it's a occasion that you don't like to miss. We're going to have prizes for the best posters that were presented, and we look forward to that. So for now, we can take a break. We have tea already set for us, just like the previous days. So 15 minutes, and we should be back for the next lectures. Thank you very much.
summer school. It's a period of 2 weeks from 5th to 17th. So far, we are at the third day. It's been so far we've learned so much, and hope period we find achieve. From 5th to 17th of May. So far, we are at the third day. It's been insightful. We are networking. We have talks like from people from all over the country, from Italy. We've met people from Germany, people from the Max Planck Institute research group, and so far we've learned so much, and hoping by the end of the period we'll have learned and obtained a lot of knowledge.
My name is Hilary Aradi from the University of Kabianga, currently pursuing an MSc in Physics, Optical Fiber Technology option. And I'm just thrilled to be here at the MMU University, courtesy of our school attendance. I'm here to attend the East African Summer School of Optics and Lasers. And so far the interaction has been very productive. I've been able to interact with scholars from various institutions, whereby I've been able to learn a lot from them. I'm just thankful for this opportunity. I'm thankful for the hosts, that is the NMU, together with the partners ICTP and the NEO Lab, for the opportunity, and I'm looking forward to a more positive interaction, to a more intrusive and more interactive session with every scholar and even the organizers of the program. And definitely we are going to move on together as scientists, and we're going to move together as a unit, all in pursuit of academic excellence.
Hi, my name is Jabet Raquel. I just finished my Bachelor of Science in Applied Optics and Lasers. I'm currently a participant in the East Africa Summer School for Optics and Lasers, and this is currently the third day. I am enjoying the lectures from various doctors and professors. I really like how it's diving more into female speakers, which is giving us the motivation to venture into the optics and laser field. This summer school program has really helped me in gaining a better understanding, and I really enjoy and looking forward to what they have in store for us.
Well, thank you so much. I'm David Kaile, and I'm from Multimedia University. I'm an MSc student, in other words, a Masters of Science in Laser Technology, and that has been a wholesome experience to gather a lot of information concerning optics and lasers in the Easter Summer School Conference. And I can tell you it has been a wonderful one. In fact, we are still waiting for more. By the end of this conference, I'm targeting to have gathered a lot of information concerning my field and also what I aspire to have in the nearest future. Remember, doing Masters of Science in Laser Technology, I'm also aspiring to have my doctorate in the field of photonics, and how I wish to gather a lot of knowledge from the resourceful people who have just come in, including also the president of Optica. That one is amazing. Thank you so much. I hope you are still enjoying also whatever place you are. Just follow us online at Multimedia University in the YouTube channel. Thank you so much.
have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials, and present research findings to scientists, ensuring safety and quality standards are met. our Laser and Optics Lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our radio. We have our own radio station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.
A laptop is an essential asset in the modern society. However, many of them are lost as a result of theft taking with them vital information. But now comes Electracker, an online system that gives users the ability to register various electronic devices using their serial numbers. To access Electracker services, visit the website, create an account, log in into your account, register the device serial number. In case your device is stolen, you report in the portal. Electracker will then help you track and recover the device.
I had lost my laptop, but thanks to Electracker, I found it. Asante sana Electracker.
Electracker helped me track and recover my lost laptop, which was stolen on my way to school. Wewe pia jaribu Electracker, cause iko fiti.
So you don't want anything that is reflective on your hands, not even a watch, because otherwise you might have reflections that you are not controlling, and it can be dangerous. Okay. Right now, as I said, this one is not an hazard, but in general, it's very important that you work in a safe way. Let's take our cylindrical lens. So I'll show you this one. So this is a cylindrical lens. Maybe you can have a look. So you see, it's I don't know if you can see what I want you to see, but here it's flat. Okay, this side, can you see that it's like a cylinder? All the efforts, can you see that it's curved in one direction? You can see, right? Okay, it should be quite obvious. Can you see? So you don't touch the lens. Now I have your fingerprint. Can you see the fingerprint? So that's bad because you have everybody has oil on the skin, which is fluorescent. So if we are working with fluorescent, we have to avoid as much as possible to have contaminations. And also this can, destroy a little. Not destroy, but like everything is very, the coating, everything is very precise. Now there, where the fingerprint is, what will happen to the wavefront of this, very bad. So, the thing is also, you would say, well, just clean it. It's not that easy to clean it, huh? You need the cleaning tools and then specific products, and sometimes some of the optics have coatings that you can damage if you clean. Okay, so for example, if you have a dielectric mirror like the one that we were talking about today, when the other lady that was talking about compression with the dichroic mirrors, with the multi-layered mirrors, those mirrors are really expensive. You don't want to get them, you don't want to touch them. You stay away from my dichroic mirror. And if you try to clean them, you might ruin the compression of your pulses. So it's really something that you shouldn't do. Well, now it's done. Yeah, exactly. So I'll show you. So if I mount here this lens, okay, this mounting that I have placed here, it is a mounting that can rotate. Okay. So let's see what happens. Okay. First of all, let's check with a piece of paper. So we check in a controlled way. So I'm here. I'm very close to the lens, and there is nothing to see. But if I go in the focal plane, look, I have a line. Can you see?
Yes.
So the focal plane of this lens, it's a spot. It's a single dot. Here, the focal plane, it's a line. Okay? Why is that vertical? Here it was round, here it's round. Here it's horizontal, and over there is vertical. First of all, if we think of this in 3D, it's a plane. Look, you can see the plane if I do this. Can you see that it's a plane?
Yeah.
Okay. If I rotate the cylindrical lens, so I'm rotating it, you can see I can rotate the beam. Okay, now it's vertical. If I do like this, you can see even better, probably that this is a plane. Can you see? Okay, in the other direction now. Okay, so if I rotate while I move, you can see it nicely. I have a trick. If I have time, I will show you my trick. My trick is use, I'll show you later. Yeah, it's a nice trick though, so I want to show you. Let's go on. How large it is here in the focus? Somebody can read?
About 0.8.
Yeah. Are you sure?
Yeah.
Okay, so then you tell me. Okay, so how large was it here?
0.7.
Hello, we want to start. And before we start, we would like to go up there and take a photo, a group photo. Now.
The 10x objective, it will magnify 10 times, and it has a 0.28 numerical aperture. Do you think this is a large number or not? It's not. It's not. A good 10x is 0.4, usually. At least 0.3, come on, this is 0.28. Why? Well, this objective has the pro, it has a good point of being long working distance. So the focal length, it's very long. So this gives me the opportunity to mount in a three-dimensional manner my sample. So I have space. I don't need to stay here very close to the objective. I can have something that is very big. If my sample is 1 centimeter, I need to be able to move it around, for example. So I want to have room. If I was using a very high NA objective, I would have a better resolution, but good resolution is not everything. Because maybe you want to see a large field of view, which is usually what I want to do. Larger field of view. Anyway, so what we will do? Today I told you that the objective has many lenses inside. Why?
Chromatic aberration.
Exactly. So all those lenses are needed, okay, to have the right magnification, to collect as much light as possible, and to correct aberrations. In particular, chromatic aberrations. So this is a plan apo objective. Apo stands for apochromatic. It means that it's corrected for a broad range of wavelengths. Still, if after this I put a lens that is not corrected chromatically, I mean, this is useless, right? So this one is not a single lens, it's not a thin lens, it's not a single one, it is a triplet. It's probably at least a triplet, meaning that it's at least 2 or 3 lenses all together, put all together. so that chromatic aberration
Yeah, good morning, everybody. Good morning. Yeah, it's another time that we have our second speaker, Professor Muhammad Kasim, from the University of Information Technology, Pakistan. Professor Kasim did the PSc degree in electronic engineering from the International Islamic University, Islamabad. Then later he proceeded to do his master's in science in electronic engineering, and later with a PhD in electrical computing engineering from the National University of Singapore. His area of research or area of interest is in optics and nanophotonics, nanofabrications, and metamaterials. Allow me to welcome Professor Kasim to take us through this session.
Okay, till they fix the projector, so I would like to interact with the students a little bit. So that day we had some initial briefing, what exactly we will be doing in terms of all the teaching and training sessions throughout this school. And that teaching and training session, the first thing is today. So okay, now it's okay, so I will show the slides. Okay, so thanks Dr. Ogaro for the nice introduction. So as Ogaro mentioned, my name is, you can call me Kasim. So I am Associate Professor and Chairperson in Electrical Engineering Department at Information Technology University, Pakistan. So, although the topic is matter and flat optics, the way I described that day as well, I realized after discussing with the students a couple of things. Number one, there are quite a mixture of students coming from undergraduate, from masters and PhD. I think very few from PhD. So I kept the level very basic. So it's, even if you cannot pick, I'm here for next 10 days, so we can still discuss and learn during other sessions as well. Second important thing, because I realized the students do not have background in metamaterials, so what I decided that first half an hour to 45 minutes, I will be describing about what exactly are metamaterials, and then taking from there to what's the difference between metamaterials and meta surfaces, and why we call this meta surfaces as meta optics and flat optics. I think my introduction is more or less done, so I will skip this. So because Optica president is here, so I would like to mention that I'm also, we also have SPI and Optica chapters, and I'm advisor of these chapters, and we do range of activities, which I think I will show the glimpse of them. Okay, so we work in a team, so team of various PI, 3 to 4 PIs, under the label of Innovative Systems and Solutions Laboratories, out of which Micro Nano Lab is the directly under my control, and then various other areas like bioimaging and sensing, AI and computation, smart energy and photovoltaics, environment and sustainability, and then we lately jumped into STEM education and additive manufacturing. Most of you have seen yesterday a few of the initial prototypes on which we are further building upon. So we are more towards applied research, so working very closely with, you see, it's from research to innovation and trying to liaison with the industry. So we work with strategic organizations to design mostly customized solutions for RF and microwave. For healthcare, we work with the local medical facilities in terms of disease diagnostics. And for education, recently we had a couple of meetings regarding the STEM education and developed some cost-effective solutions for the local public schools. And then there was like IoT sensors network, flexible and electronic sensors, and a few of you who had seen the poster yesterday as well, so different applications. So this is just a glimpse of few projects. In terms of what we have and what we do in collaboration and what we do outsourcing, so we are basically fabless modeling and design you see team. So I think this is pretty suitable for the developing world. Anybody sitting in the developing countries, it's I mean, you do programming, you use mind, computation and all that. This is much easier to do. So we have this a long history of running this fabless cycle with various international collaborators. Most of the works I will be showing during the lecture from here to onwards. Then bunch of trained human resource. We do focus on the building capacity in collaboration with foreign collaborators and obviously local industry. And computational resources for the you see servers and such kind of licenses, so on and so forth. For the characterization and testing, yes, if we can do by ourselves, we do it, but if it is not possible, then again we go back to the collaborators. Device and system level prototyping, this pretty much now for the additive manufacturing, we are trying to develop capability in-house, but obviously for some advanced stuff, we rely in hybridization mode. And commercial design tools like computational tools, so on and so forth, which are very expensive, we can still collaborate with external partners. Something which we really outsource is nanofabrication, and obviously we build some linkages with industry and technology readiness, which is exactly what we want towards the end. Okay, this is, I had pretty much explained. So that's why for the students, I would say you take it as a complete package. It is like 18 plus 6, 24 hours of teaching and training. That involves actually 3 talks. So one is on meta optics, flat optics, and then there will be on computational photonics. For the additive manufacturing, you have seen it is like optical system design, conventional, and then it will be packaging, how we do the CAD designing for those kind of optics. And then for meta optics, we will be looking into how device level and system level optimization through computational tools, through AI, and through ray tracing. This is what we will be looking into. And then how we can use AI modern techniques for the healthcare diagnostics. So these are like 6 more or less practical sessions will be there. So I would like to acknowledge we put lots of effort. There was a big team working on the preparation and the training and building the manuals. And I would also like to acknowledge Kenyan students who were also part of the team during all this process, and we have been like putting lots of effort since 1.5 months into that. Okay, because I'm like student centric, so that's why I would put more towards basics and motivation, why you need to do optics, why you need to do meta optics, and so on and so forth. So optics, what are the opportunities? and what are the markets you can get job into if you are working into applied optics. So I have taken this snap from European Photonics Consortium. So it is like optics is always branch of physics that study light and its behaviors. In terms of market, it's from medical, material, manufacturing, and communication platforms. There are a range of opportunities, industries. So if we look into like agrivoltaics, you see AR, VR, medicine, medical, defense, there are countless opportunities in terms of job market. So to further, like optics is an amazing field to be involved in. So I put salary, you see survey from global salary survey report from SPIE. So actually it is not very easy. These are like different markets in terms of defense, semiconductor industry, so healthcare, and later I think you will also see the slides. I mean, in terms of numbers, it's like you can make lots of money if you are expert in real applied stuff in various industries. And very interesting thing in terms of various markets, in terms of salary growth, you see particularly if you look at the Chinese, with every year, I mean, median salary is increasing, so that is also a very growing market in terms of job opportunities. And for the other, other areas, it's like pretty consistent in that term. This I just put like optics has a great future. Make sure you don't shy away from asking things you don't know. So another, if you want to judge if the field is good or not, so very important key factor is sustainability of career in that particular domain, in that particular area. So if you look into numbers in different regions, so you see with the experience, you get a very decent career growth in optics areas. So this was like a bit about why you need to do optics, what we are doing, and what we will be doing in the next like 10 days. So before moving forward on what exactly are metamaterials, we will look into EM wave solutions and refractive index first. So refractive index obviously is a complex number which has real and imaginary part. So refractive index is like real part. It controls velocity and you can say phase as well, yes, through the medium. And if you want to write the phase constant, it is like beta is wave number into this real part, and excitation coefficient is the absorption inside the material, loss basically inside the material. So the relationship between refractive index and permittivity and permeability is something like this. So over here we need to keep an eye, a very interesting thing. So square of refractive index is basically mu r epsilon r. So now if we take the square root, so there should be mathematically, there should be two numbers, plus and minus, right, with this epsilon mu pair. And their relationship with electric and magnetic susceptibility should be something like this. So now what are the possibilities in terms of sign conventions of epsilon and mu? So there are four obviously possibilities. Both could be positive. One of them could be negative, and it could be the case that both of them are negative mathematically if you look into this thing. So this is, let's say, for the electromagnetic wave, obviously there is electric field as well as magnetic field. So this part, which is due to the extinction coefficient of the material, that is basically a loss, right? And this one is phase. So if we want to see the fundamental characteristics of a wave, so we have like three: polarization, amplitude, and phase. Polarization is like, okay, one thing, and then magnitude is actually dictated by the extinction coefficient of the material, whereas this phase or velocity of the medium is dictated by the refractive index. And if it is lossless, the wave will go this way, and if you have a lossy medium, obviously it will decay along the propagation through the medium. So, I mean, further relationship between refractive index and permittivity, permeability, you know. So now if we put these four combinations into wave equation, so what will happen? Now I took lossless medium, I take K out of the picture to see the impact of like these four cases. So if both of them are positive, so we have phase over there, so we have complete wave, and it is like forward propagating wave. It is propagating in positive direction. And if both of them are negative, you see, negative, negative, negative square, and you get negative. Now you still have phase term, right? But sign is reversed, which means now the wave is propagating in the backward direction instead of forward direction. However, if one of them is negative, then you end up with real part, which means it's pure loss. So once a wave entered into that kind of a medium where one of them is negative, so you get a evanescent wave, no transmission, no propagation. Now this is like very famous mu epsilon mu diagram. So these are like four quadrants. Now if we look at over here, it should be like both positive, right? First quadrant. Over here we should have mu epsilon negative, mu positive, and over here epsilon positive and mu negative, and this one is a very interesting thing where we have both negative. So we call double positive, epsilon negative, mu negative, and double negative materials. So we can, in the mu epsilon diagram, this is how we can put all these materials. Isotropic dielectrics, abundant in nature, both double positive materials, we can find lots of materials, all of them, like majority of dielectrics. Then for the metals, yes, below the plasma frequency metals behave like a metals, and real part is negative, which means metals at optical frequencies fall in this epsilon negative medium, this second quadrant, and obviously in metals we do not have propagation, it's a evanescent wave, right? Over here, mu negative, still no propagation, evanescence, sorry, there is a typo. So there are very few natural materials like ferromagnetic material, but not abundantly available, but still there are some natural materials available in this domain as well. So now if we look into this, all three quadrants has some natural materials. This thing is very interesting. In nature, there does not exist any material which has both epsilon and mu negative at the same time. So you see, and later we will further look into what is the advantages of having this kind of double negative material where we can have backward propagation, so on and so forth. So until here we decided that there are four types of material, and there is one section of materials which is not available in the nature. Such kind of materials we also call right-handed materials, because you see it follows triad of right hand, you see E, H and K, and such kind of materials we call them left-handed materials because it follows the triad of left hand. Now what are metamaterials? Metamaterials, the word is actually combo of two words. One is Greek, meta, which means beyond and after, and material, Latin word materia, which means matter, means beyond natural materials. So if we look up front in the mu epsilon diagram, immediately our mind will go that third quadrant, left-handed materials which are not available in the nature, those should be part of metamaterials. However, this was like initial stuff, and later on, you see, this metamaterials thing does not have a now well-defined generalized definition. So we say anything you can artificially engineer, which can exhibit phenomena or properties which are not available through naturally occurring materials, we will call them metamaterials. So in principle, yes, three quadrants have natural materials, but we can still build metamaterials in those domains as well, and materials which are built for the third quadrant, they are pure metamaterials. So this is like generalized term. So where we have, for material we have atoms, for metamaterials we have meta-atoms. The difference is the size. Atom size is very small. Let's say if you talk about classical electromagnetics, so you see for a visible light you have, let's say you take 500 nanometers, atom size is very small. But to engineer this wave matter interaction, you have to have this meta-atoms comparable to the size of wavelength, slightly lesser than wavelength, but it cannot be very small. So metamaterial is basically arrangement of periodic or aperiodic arrangement of meta-atoms in two-dimensional, in three-dimensional, but they are artificially engineered. So we take away from like EM, yes, we can engineer through metamaterials this light matter interaction for EM metamaterial, electromagnetic metamaterials, but we can build several other types of metamaterials for acoustics, for thermal, for master mechanical, so on and so forth. Now you see, it's more like a hybrid of, you have some base material, let's say it's air, it could be glass or something, and then you put some other material on top of that. So it's more like a composite material, and now you build some effective mu and epsilon, effective permittivity and permeability by yourself, and you can engineer by changing the physical parameters of those geometrical structures. Wow. Okay. This is, I am putting upfront what is motivation of studying metamaterials, what are like applications for them, and then after learning some basics, I will put this slide again, once again, to get you deep into the motivation of learning metamaterials. So you see, for this kind of anomalous behavior, instead of, you see, conventional refraction, we can have now negative refraction. Later on we will see how, which can, then we can also build some, you see, epsilon mu effective mediums, epsilon near zero mediums, epsilon, you see, any type of epsilon and mu combination, and applications could involve in invisibility. You can make some, you see, I can see you because there is a reflection of light coming to me. So if I can divert this reflection, you are invisible to me. So a very simple thing is, if I have something and light goes, and if detector is here, you can see. But if it does not come back, you cannot see it, which means you can make a thing invisible. I just put some crops from news, how metamaterials could lead to invisible tanks and super stealthy submarines. You see, look over there. So they have lots of applications, particularly in the strategic organization, and obviously for some other civil applications as well. Similarly, there are acoustics metamaterials where, for example, in the industries, they want to absorb the noise, to reduce the noise. So you can have such kind of acoustics absorbers, ultra thin sheet-like absorbers, which can, you see, absorb the sound and eventually reduce the noise. So actually this is not something in the books. There are lots of companies like Sonoblind, Meta Blockers, so on and so forth, who are actually building metamaterials for the industry for this reduction of noise. Then it comes to meta optics. This is also like one, you can say, a special section of metamaterials where you can have flat or ultra thin metamaterials. And as I have mentioned in that session as well, so if you want to have a microscope, let's say, integrated into your mobile phone, if you want to have a metaverse, AR, VR sets, something like a glass, so you need something very, you see, compact, ultra thin kind of thing. So such kind of innovative solutions are possible through metamaterials. And I have listed bunch of companies which are actually producing metamaterials for industrial grade. And this is like global metamaterials market forecast. So currently it stands at 330 million, and if it reach 2030, it will reach to like 1 billion. So there's a lots of opportunities in terms of if you are good at designing something really good. I would also, later on I will also mention, but you see, most of the people who are in academics and still wanted to have some kind of spin-off and so on and so forth, this is something really possible. You see, I mean, there are always two different things. One, modeling and design, and then fabrication. You go to the foundry. Foundry cannot be hosted inside a university. It can only be done by the industry. Universities are for prototyping, for doing all those kind of things. But for metamaterials also, there are companies who actually model and design. And then they are, you see, linked with the foundries to now going back to some basics. We learned the motivation and job market and possibility and future of metamaterials. So this whole story was started with Professor Victor, who was a Russian scientist. In 1967, he predicted that substances with some at the same time negative permittivity and permeability, there could be some natural substances, but his prediction was, since at that time nothing was known regarding metamaterials, his prediction was there could be some substances which can exhibit that kind of properties. And then this statement was like very interesting at this moment. Unfortunately, we do not have even a single substance isotropic which could be isotropic and have negative permeability. And he called such kind of substances having both mu and epsilon negative as left-handed materials. This is like first definition which he gave. And obviously, as I was mentioning earlier, so having left-handedness will reverse the tiro from right hand to left hand between E, H and wave vector. Several other fundamental phenomena in association with left-handed media he also predicted. For example, reversal of boundary conditions, where at the end of this lecture we will see the normal components become anti-parallel, reversal of Snell's law, negative refraction. So changing point source into point source, it can be used for a lensing and imaging, you see, point source into imaging, and interconvergence of, you see, making convex lens into concave and concave into convex lens. These were like just predictions. So I will skip most of the math from here, just to going into the basic. So you see, this is like atom in equilibrium state, and this is atom once electric field is applied, right? So it follows Lorentz oscillator model, and this is like Newton's equation of motion, well known from the basic physics. Over here, so this is like, I want to show something. So real and imaginary part of, you see, for epsilon, for Lorentz models for dielectrics, right? So if you look at like real part, right? So we have the region we have the region where real part of permittivity is negative, right, from the Lorentz model. Now, for a given, any given natural material, that part where this epsilon stays negative, it is fixed, because for any natural dielectric. Now, if we remove this restoring force for the conductors, which is the case because we do not have like elastic, vibrating, oscillating electrons, so this will go out, and then expressions for epsilon real and imaginary becomes like this. And if we plot them with frequency, now you see imaginary part, real part is like this. So this is how, this is the cutoff point, which is plasma frequency. So below plasma frequency, metals behave like metals, and if you go far away from the plasma frequency, so metals also become transparent, right? So what I said is there is a portion of frequencies where you can have negative epsilon for the dielectrics as well, and obviously for metals you can also have, I mean it is by default negative. So this is like plasma frequency for various metals, that cutoff point, that if frequency is higher than that cutoff point, that metal will be eventually, I would say, less lossy. Okay, now this is from nature, Lorentz and Drude model, response from a natural materials. Now, back in 1998, John Pendray presented this like artificial permittivity. Now, what he did is he used this kind of cylindrical wires to realize negative permittivity. Now, but if you look at this plasma frequency, electric plasma frequency, it is dependent upon the features, you see, geometrical parameters of these cylinders and periodicity, so on and so forth, right? What does that mean? If you make a if there is a natural material, so this cutoff frequency is like fixed, and range of that window is also fixed. But if you have such kind of artificial permittivity, what you can do is you can tune this window depending upon what kind of parameters you want to set. Yes, eventually once you fabricate it passive, but you can also make such kind of metamaterials that active, where you can actually shift this frequency window. So this is like artificial permittivity. This was like then 1998 by John Pendray. This is artificial permeability. Now we remember that natural materials, as Professor Victor mentioned, there are no natural materials which can exhibit negative permeability. So this was like artificial permeability. So where he has used this kind of split ring resonators. So if we look at this magnetic frequency, plasma frequency, and if we look into the response over here. So now you see we have a window of frequencies, range of frequencies, where mu is negative, and this mu negative is achieved through artificially engineered materials. It is not coming from some natural materials. Now you see we can make artificial permittivity through metamaterials. Now we can also make artificial permeability through metamaterials. What was not available in nature? You remember that mu epsilon diagram where both of them are negative, right? Right now both of these materials, one is epsilon negative, one is mu negative, right? What was not there, both of them are negative. So back in 2000, D.R. Smith, he demonstrated such kind of metamaterials where actually he combined those cylindrical rods with split ring resonators, and then this was like very interesting. So you see this is what, like epsilon negative region, epsilon negative region, and this is mu negative region. You combine both and you see the shaded region is where both of them are negative. Now these metamaterials, artificially engineered, they can give us effective epsilon and mu, which both of them are negative and they are left-handed medium. So looking into boundary conditions, this is now, it will go on for like very long lecture, so I will stop here and then I will start like flat optics. Okay, so if we look into the boundary conditions, as I have mentioned, for if you have both right-handed mediums, so you see normal K wave vectors, they are parallel, but if you put like right-handed and left-handed, they are anti-parallel. And now if you have this kind of interface between right hand and left-handed medium, instead of, you see, if it is a conventional medium, it would have gone this way. It came that way. So this is like negative refraction. Immediately it can go into this kind of lensing. So where you see you impinge light at the interface, instead of going that way, it will come back, right? And then if you use another boundary, so what you can do is you can image the source over there, right? You put some object and you can get the image. So this kind of NRI, negative refractive index materials, can be used as a flat, as a lensing, for the lensing. And there are lots of demonstrations for this. Similarly, as I have mentioned earlier, if it is a right-hand slab, convex will behave as a convex, it will converge, but if it is a left-hand material, it will diverge. So reversal of these properties. Now I think we can pick what I mean for negative refraction, for invisibility, for cloaking, for squeezing the size, and designing the flat absorbers, so on and so forth. So we can build any kind of properties through such effective mediums. Okay, Jared, second plan. Should I stop or continue? Okay, this was like, yes please, if there are some questions. Yes, yes, please.
Okay, thank you so much for that presentation. It was a good presentation. Now, you've seen that the difference between the metamaterials and the materials is about the atoms. The metamaterials have the meta atoms, while the other materials have the normal atoms. So, can you maybe to tell us some of the examples of the meta atoms that are used for making the meta materials or meta optics, please?
Yes, I mean, for example, this one I have shown. All of them. We start from here. You see this. This is one type of metamaterial. You are using periodic cylindrical, you see, rods to exhibit artificial permittivity. This is like another one. We are using this kind of square ring resonator to realize, again, artificial permittivity. And then there is another type of meta atom, split ring resonator, to realize negative permeability. Now I would like to actually, linking back to your question, if you look over here, this is like one meta atom, right? And we arrange, we have a periodic or aperiodic, you see, distribution of such meta atoms to make this kind of metamaterial. I hope I answered your question.
question?
Okay, thank you, Prof, for the good presentation. My question is on the application of metamaterials. You said that acoustic metamaterials can be used to absorb noise. Can you briefly explain that concept, please?
Yes, yes. So you see, in order to absorb the material, so you have wave, and if you can add some additional phase while it's reflecting, and that additional phase is kind of exactly out of phase, so overall reflection will die out. So very simple. It could be done through thickness, it could be done through resonance, it could be done through adding some additional phase at the surface. Yeah.
Questions?
Yeah, thank you. When you talked about negative refraction, that reminded me, in order to get this negative refractive index, you need this artificial meta structure. So on the slide it looks nice, you can bring the rays to a point, but of course the structure, the scale of the structure limits this. So, and then I think, if I remember correctly, this negative refraction you only have in a certain frequency.
Yes, yes, for the range of frequency.
Can you tell me what is the current state? I mean, how fine is to what level is the best negative refractive material available so far? To what level is it homogeneous? To which length scale will it actually focus? And are there some that are fairly wide bandwidth? So what is the status at the moment?
Yeah, actually there are now lots of things making them, after this you see it was like 2000 and so on and so forth, lots of demonstrations to make this window broad, also make it like tunable, putting some diodes and so on and so forth. Yeah, so this is pretty much now people are doing, and there are lots of demonstrations in terms of super lensing, where you can focus this into a very tight spot which can break the diffraction limit. Yeah. So in terms of that domain, it reached to that level.
Mike, I just have a simple question. From your presentation, it appears to me like these metamaterials, they're kind of limitless. Which brings me to my question is, are there any natural fundamental limits to the capabilities of these metamaterials?
Okay. I would say this limit is dictated by the, technology, what you can fabricate. So in terms of design, you can design whatever you want, right? But limit is, for example, if you are making a rod, let's say if I say some nanomaterials, which has a very, which is very lengthy, and the feature size is very small. Maybe it gives you some real cool phenomena or output, but now it comes towards the technology, whether this can be fabricated or not. So I would say that limit is in terms of technology. Yeah.
They're asking if the permeability coefficient have a significant impact on the resistance of the material. If yes, at which level?
Oh, okay. You see, mu and epsilon, they are into that phase kind of thing, right? So when you say resistance, I will talk about absorption and loss, right? That is towards the imaginary part, nothing to do with the real part. So what we are talking about is real part of mu and epsilon. That's why when I started, I taken this lossless to make things easier.
Any more question?
Perhaps next lecture is long, so if you allow me, we can start that one. Yeah,
Just last one
yes,
question.
yes, please. Yes.
Now, when you compare ordinary flat optics and metamaterials, what is the differences in terms of precision and
Okay.
flatness?
Yes. Now, I will talk about flat optics or meta surfaces. They are different. Over here, we were playing with epsilon and mu, while for the flat surfaces, meta surfaces, we will be playing with reflection, transmission, and adding phase at the surface. So the basic, you see, motivation is different. We are not doing epsilon mu effective kind of engineering for meta surfaces. Instead, it's all about engineering at the surface between the two media. I will explain actually now. So I think this will also help all of us to kind of differentiate how meta surfaces, they are different from metamaterials. Yes, they are kind of subsection of metamaterials, but their kind of main motivation is different. Second one? Second lecture. I will try to cover all of them. So even if I skipped few slides, I will be there. I will be very happy to talk with you students. Okay. I hope you are picking what I'm saying, right? Very good. Because if you are not picking from here, it will be very difficult for the upcoming sessions. Okay. Okay. Now, in terms of flat optics, I will say a few names and all of them are used. Number one, flat optics, meta surfaces, meta devices, ultra thin surfaces. People use different names, but its thing is same. Okay, so that's why I put meta. Now we can say material, meta, material, something beyond natural material. So meta surface, it will be some surface which is beyond natural surfaces, right? So we can also call it flat. So yes, we can call them, actually two-dimensional is not a correct terminology people say in literature, because two-dimensional means you have single atomic layer thickness. I would say planar metamaterials. They can be classified as meta surfaces. So now if I use like meta surfaces, meta devices, meta optics, flat optics, everything same, okay? So in contrast, to play with mu and epsilon, as I have mentioned, we will be playing with the ultra thin surface. It's just like a sticker, you imagine. So you have one medium, it's a water, and you put some kind of sticker, ultra thin sticker kind of thing. And now playing with this sticker is basic motivation of meta surface. Now it's not like we are playing with the mu and epsilon. Yes, effectively we are doing, but basic is playing with the interface. And once you play with the interface, at the interface between two media, two things can happen. What do you think? Reflection and refraction. It means we will be engineering reflection and refraction. Okay? So now you see, if I take two medium, air and water, I put source, detector position should be fixed, right? Source and detector, because between two media, angle of refraction will always be same, right? But now between the two media, I put meta surface. What can I do? I can throw my reflection anywhere I want, breaking the Snell's law, okay, anywhere, not following the Snell's law. So now you understand the main difference between. Similarly, if I have like two materials, again angle of refraction is fixed between the two materials. But if I put some surface at the interface which is ultra thin, sub-wavelength, and I can play with the refraction. Now you just imagine if I have a tunable surface, what I can do, I can play anywhere I want, and I can also throw energy instead of one direction in multiple directions, right? So this behavior is anomalous, it's unusual, right? So this is the basics of meta surfaces. Why I want to discuss, so you can link, it should not be only math and doing some phenomena, because there are some undergraduates, so I just put optical components, lens, prisms, so on and so forth, mirrors, I hope you know, coatings, these are like optical components, lenses, convex, concave. I will not show the details obviously, I hope you know, but just to link. Then what's difference between a one convex lens and machine vision lens, objective lens? I hope you know. So in objective lens we have series of lenses, so it's a system of lenses, it's a lens train, it's not a single lens, right? Something like this. Now it depends how many lenses and functionalities you add. You see, let's say you build achromat, plane achromat, fluoride, plane fluoride, plane apochromat. It depends what kind of, you see, aberrations you are removing in terms of, so in other words I will say putting more lenses obviously to enhance the imaging as per the requirement, but at the cost of obviously finances and also design complexity. And this is like lens assembly, and these are like optical components, and then I said system of lenses to make objective lens, and then systems. So lens to system. So for example, if you say camera, you say microscope, again it is not single lens, it says train of lenses, right? It's a train of lenses, and then on top you have camera. Camera is again, you see, train of lenses. Let's say if you say bigger camera and so on. So optical systems can be characterized in two types, imaging and non-imaging systems. Now if I say the name microscope is example of everybody, imaging system, right? Camera is an example of imaging system. How about laser? It's not imaging system, right? So that's a very simple classification. So I will skip that, how it works. Camera, you have system of lenses, sensors, so on and so forth. So now I will skip, now we already know. Now for flat optics, where it fits in. Okay, now let's compare. I have taken one, you see, biconfocal lens from Thor Labs, and I opened its CAD file. You just see thickness. How much is that? 4.2 millimeter. And working wavelength is like 350 to 700 nanometer. So if I write in terms of lambda, this thickness, it is approximately 10 raised to power 4 lambda thickness of the lens, conventional lens. That's why I said any imaging system contains train of lenses. So if one lens is that much thick, so you can imagine that a microscope, DSLR cameras, they should be that much thick, telescopes, because the fundamental unit is very thick, bulky. In contrast, for meta lens, you can build a meta lens of thickness equal to lambda or even less than lambda, right? Because it's a thin sheet between the, later we will see further into that. So it means for a device level, you can get size reduction of like 10 raised to power 4 lambda. Now I mentioned, let's talk about objective. It is train of lenses. Another big advantage this meta surfaces or meta devices give, you can put, you see each lens has certain functionality, right? Certain phase, in other words. So you can integrate multiple functionalities into a single chip for a meta surfaces. So again, I took another CAD, and you see its thickness for the objective lens was like 45 millimeter, and in terms of wavelength, it was like 10 raised to power 5. And again, if I make meta-objective lens, I can again make it an order of lambda, which means it can give me a size reduction of 10 raised to the power 4 to 10 raised to the power 5 lambda. That's why I was saying in the beginning, now if we want to have on-chip microscope, if we want to have on-chip DSLR cameras, if we want to have AR, VR sets just like this, sticker, or very small, meta-optics is the solution, and it's the future. Compact opticals. So this is not from me, it's from Synopsys. I hope most of you know it's a big company, computational design software company. Meta-optics have the potential to revolutionize optical products by replacing bulk curved surface elements into thin surfaces, and so is true that it can help to squeeze the system to realize on-chip meta-optical imaging systems. So meta lens is a key enabling technology for the next generation of compact imaging, sensing, and display applications. Again, this is not in the theory. Believe me, there are lots of opportunities if you know how to design according to the given specifications. So this was like first company that popped up named Meta Lens, and actually this meta surfaces theory was started by Professor Capasso back in 2011, and he is like co-founder along with his student. It's a Meta Lens company. So if you look over here, this is like very interesting if you can read. What's written? We are a fabless semiconductor optics. So what they do? They coordinate with industry, and then foundry, they design according to the requirement. And over here, what's written? Combine the function of 5 optical elements into a single meta device. This is what I was saying. Converging multiple components into a single. They are building, you can look at their products, markings, lots of very interesting things they are doing. This is another Chinese company's Meta Lens X. Again, you see, they are building such kind of meta optics in consumer electronics, LiDAR, optical communication, and customized solutions for real industry. And I was in China in December and January. There is lots of demand for, you see, meta optics designer, because this whole field is really growing. And then you see there is another company, so this is again for design, pure design company. Now you can understand there is an industry which really wants such flat products, and they need designers, good, fast, rapid designers. Okay. I hope we learned the motivation and potential of meta optics, why it is very timely to get into this technology. There is a future in this, to be honest, in terms of jobs and that. So I have explained already that difference between conventional and, I would say, generalized Snell's law. So we will learn a bit of physics of this. So you see, since phase over here, if we look at, you see rays coming and hitting this convex lens, they are converging, which means they are meeting at this point in phase, right? Look at two rays. What do you think if I take this central ray, if it would have been a flat surface, if I look at the central ray, and if I look at the ray coming from the edge, do you think the distance these two rays covers it same? These two rays coming from the center and coming from, let's say, somewhere here. There is a path difference, right? There is a path difference. Okay. So further you are, path difference is more, right? So what does that mean? We want all rays to reach at this point, at the same point, in phase, at the same time. It means we have like 3-4 people. We want them to run, but also want them, so one has to run a larger distance, one smaller distance. So if medium is same, let's say air, it's very obvious the one who is covering the shorter distance, it will reach earlier, right? So if I have to make that both of them should reach at the same point, what I have to do? I have to slow it down the person who has to run the smaller distance, right? I have to slow it down. How to slow it down? Now if we say, if we have a wave, where it has a maximum speed, velocity in the air, right? And you put it in some index medium, velocity will go down, right? So that's why if you look at the center part is very thick. Why? Because the distance it has to cover is much lesser in comparison to the one which is coming from the corner, right? So we have to kind of maximally slow the center one, and then depending upon the, you see, location, we have to slow it down accordingly so that all the rays meet at the same point, right? So now this kind of, you see, phase control is achieved through curve shapes in the conventional optics. You slow it down by using thickness, right? Thickness, and I would say material. So I will say N into D means refractive index and how much you want a wave to travel in that particular refractive index, and you control the speed, and then you control the constructive and destructive interference. However, once we talk about meta surfaces, what we can do is, you see, it's a sheet of such sub-wavelength resonators, and these resonators have different geometries. So different geometry. Each geometry gives different phase. You now look at in terms of speed. Each shape gives a different speed, I would say, in a crude way. So now you see what we can do is, by changing the geometrical structure of sub-wavelength resonators or antennas, what we can do is, we can do the same thing, making a certain part of wave slow or let someone to go fast, okay? So you see, this is like very nice example where they are using this kind of, you see, helical phase distribution. Over here, phase getting from such antennas is 0, pi by 4, pi by 2, so on and so forth. Which means we can get exactly what conventional optics is doing through a ultra-thin sticker, ultra-thin surface. And the thickness is, as I have mentioned, it's smaller than wavelength. So that's where 10 raised to power 4 times reduction in the size comes. Now, how this thing happens? This is the statement of generalized refraction and reflection. So I will just pump in a bit of math, very simple one. I hope you have studied this thing. Now you see, this is like medium 1, this is medium 2, and this red one is that sheet, meta surface, right? This is like this one, and the previous picture which I was showing like this one, where we have a periodic or aperiodic arrangement of such sub-wavelength resonators. So you see, we can write expressions for incident, reflected, and transmitted electric fields over here. So as long as incidence is concerned, it is just like a conventional one. Look over here. When it will be reflected back, the point where it will hit, you add some phase, and that phase is coming through sub-wavelength resonator, sub-wavelength antenna. You're getting it? And that phase is over here. So if this surface would be missing from this part is gone, but if it is there over here. Similarly, on the transmission side, again we have control, and I would say this control is like XY. I mean, you see, at every coordinate position, you can have different control over phase for the reflection, for the transmission, and that control is coming from geometrical structure of the sub-wavelength resonator. Now you see I further apply the boundary conditions for tangential components. I will converge. If someone is interested, I can actually teach, but I would say we just keep on going. After all those simplifications, we end up with this kind of thing. Theta r, theta t, reflection angle and transmission angle. You see, if I make this phi r or phi t equal to 0, if I make this equal to 0, what it will become? This will be vanished, and theta I, sorry, over here it should be theta I. Theta r will be equal to theta I. So if there is no phase gradient, it's a conventional Snell's law. But if there is a sheet, then we have this additional term. Similarly, for the refraction, again, you see if we cancel this thing out, which means if there is no sheet, what does that mean? No extra phase at the surface. This will be conventional Snell's law. So this is what meta optics, meta surface is doing. But the beauty of this term is now you see you control this phase. What you can control? By controlling phase at the sheet, what you can control? Reflection angle, right? This is not possible in the natural materials, right? Similarly, you see again, if I change this phase at the surface, what I can control? I can control transmission angle, which means wherever I want to throw the reflection or refraction, I can control based upon what kind of sheet I want to manufacture. And if I can make this kind of phase distribution tunable, so at the run time what I can do is I can steer beam wherever I want in the reflection as well as refraction, thanks to this term. Okay. Now I hope the basic physics we can understand the difference between metamaterials, where we were playing with producing what? Effective mu and epsilon. However, in meta optics, what we are doing? We are controlling this sheet and phase gradient of this sheet to control reflection and refraction. Okay, so optics is refractive or diffractive. So from refractive optics, we have already learned how it is different, right? Obviously over there you use a curve shape, you use the thickness to control the constructive, destructive interferences, right? In meta optics you have this kind of, you see modular 2 pi phase functions, which you can put it on the screen at the interface. And I say you can control all. Diffractive, can we say meta surfaces are diffractive elements? Yes, you can call, but not all meta surfaces are diffractive elements. It's a type of diffractive components, but not all of them, because it gives lots of unique advantages. For example, they have sub-wavelength quasi-periodic structures, they can manipulate polarization, they can do the resonance. This all thing is not possible in diffractive elements. Now coming to what we do at Micro Nano Lab, our Center for Innovative Systems and Solutions, in terms of meta. This is our capability. We look at design, ingenious design, and we have meta atom database and you see libraries. We develop this kind of a design tool, and then meta logics, where we work on polarization meta optics, work on multifunctional meta optics and tunable meta optics. And this is where now we are heading, is from device to system level integration. So one is like you go for meta lens, meta surface, and then one is you really build a system. And then we put like three way of engineering this light matter interaction from our kind of design strategies. One is for imaging, that is meta lensing, light structuring, and meta holography. I will be very happy to discuss in detail because everything will not be, I won't be able to cover. So whenever you want to learn more, please feel free. Now, what is like steps to design a device? We remember three steps: pixel level, device level, system level. Pixel level will be meta atom. Pixel level will be meta atom. Device level will be meta surface, and system level will be meta system, right? Meta optics based system. So yes, at a pixel, and before that, obviously, let's say you want to work on a refractive optics. So for that particular window for which you want to build that meta optics, you want transparency, right? So material selection is obviously the first thing. And if you are working on absorption, then again you have to carefully look into select the material. So material selection is obviously first thing, and then this is meta atom. People also call it unit cell, right? Now once unit cell or a meta atom is optimized, so obviously we are going to control three things: fundamental characteristics of EM wave, which is polarization, magnitude, phase, right? Polarization, magnitude, and phase. So it's not like we are designing or building meta atoms randomly. Instead, they are requirement driven. What exactly, whether you want. So specification driven. And then second thing, what element, what component you want to build. So that component has a special phase mask, right? So first is material selection, then you see unit cell or a meta atom, then phase map. So phase map is actually, this SEM image is not very clear, but this is like hundreds and thousands of meta atoms into it. And then obviously characterization, fabrication, and then characterization. This, now this technology, where it has reached, now you see foundries or industry, they give some list of requirements, then you have to meet those requirements. So first step obviously will be what should be the design strategy, some underlying physics, what you are going to control, right? And then meta atom, device, system. Now I would like to share a very interesting thing. You will be thinking, oh, this is on-chip technology, how we can work while staying in, let's say, developing country. Not possible, very much possible. For designing, we use commercial tools. They are very expensive, and they take lots of time in the designing, right? Solution is you use open source tools. I put one example like me, FTTD, it's free of cost. You use, you can design, right? And you can also use AI. Now you see you are designing, for example, you are building your own library using MEEP. So what you can do is you start training your neural networks, AI models. So you have open source, you see simulation and design tool, and then you can train your AI models for a pixel level and also for device level, and you can go further to wow. Okay, till lies. For the students, are you getting what I'm saying, right? From metamaterials. So let me ask, what's the difference between metamaterials and metasurfaces? Anybody? Until light comes. It's not exam, just we discuss. What do you think? Anyone? Out of energy? Feeling hungry? Yes, I was expecting something from students. Thanks a lot. Oh, yes. Okay, anyways, so for metamaterials, what were the left-handed materials? Those who had both mu and epsilon negative, right? Left-handed materials. For meta surfaces, we control reflection and transmission through ultra thin sheet, which is placed at the interface, right? Okay, it's bad. So we were here at Jerry, how much time I had? So I control the pace. $15. 2 minutes? Oh, okay. I can, oh, okay. So I skip all this because we have already learned pixel level. So I will just show a few results and then you can ask something. So obviously, as I have mentioned, this I put some pixel level design strategies. We can use nano half wave plates, which can actually give a very cool control by achieving, you see, phase through its rotation. So we build some geometry and we rotate this geometry, we can get different phases. Yes, over here, you see, rotation of such kind of nano half wave plate, we can have a complete control from 0 to 2 pi. So now you see, whatever phase for the phase mask you want, you use that particular rotation at that coordinate axis. This is like one thing. Second, this like index waveguide, nano structured index waveguide, where we can further discuss the theory works, but as of now, you change the dia of the cylinder, you get different phase. So over there, you are rotating the bar. Over here, you change the diameter and you get different phase. Again, whatever phase you want, you put cylinder of that dia in that particular coordinate axis. And for nanobar, there are, one is rotation, that is geometric phase. The second one is also propagation phase. Here you can physically change the dimensions and you can also get different phases. So there is obviously different underlying physics for each of them. So again, you change the dimensions and then you get different phase. And once things become more complicated, if you want to put more phases, so you want one bar to be used for generating several phases. In other words, you want more degree of freedom. Then it comes dipixel, you put 2 of them, you put 4 of them, and then you have several parameters. You see rotation, their dimensions, gap, lots of control. And then you mix and match, so there are several ways. So that's why what's most important first step after material selection is meta-atom database. Meta-atom. So what is your requirement? You pick that meta-atom, okay? Because that meta-atom will give you phase control. And once second step is what kind of phase mask you want, you put that meta-atom according to that particular phase mask. So this is what I was mentioning, that previously we used to use obviously computational tools, and now we are in the process of developing our own tool, which is AI driven, and we keep pushing more and more through data driven AI, and then you see making is more accurate by adding some physics into that as well. And this whole thing in terms of design, where it goes. Now for a meta optics, anyone is familiar with PDKs for electronics, PDKs. Now you see there are countless options in terms of materials, in terms of, you see, meta atoms. PDK is libraries by the foundry. So you see, I come up with some weird material, I say, oh, this gives very good performance. Foundry cannot change its production line and fabrication processes. PDKs is, now foundries will come up with, okay, you have these materials, you have these fabrication constraints. These are the limits. You design everything according to that limit. Okay. So these are like standard guidelines coming from the foundries. So this meta optics I mentioned, it physics driven. Next side is PDKs. They will be done because technology reached to the point mass level production, because previous barrier was building large meta surfaces, you see, building them fast, building them cost efficient. Now all these barriers are gone. Now people are, I mean, this technology has been done, and now it's all about standardizing this whole process. So in terms of meta lenses, we do achromats. You see, for different wavelengths we can focus all the wavelengths at a single point. I will just now skim through because time is short. Another very interesting thing, so you see, for example, we can look very wide, right? We can look very, it's almost semicircle, right? Semisphere. But field of view for optics is not as big as our vision, right? So wide field of view, this is also thanks to meta optics, it is possible to realize wide field of, which is very important for displays, for all kind of. So this was like one of our demonstrations. You see, we go 0 to 85 with performance is very good. Light structuring, all types of light structuring. You see, for structured illumination microscope, you need structured light beams through meta surfaces. We built lots of them. This was my PhD work from where I started, and then we did lots of demonstration. This was, by the way, just like DHM, it's inline interference. So you see, this is for RCP, and there is some cross polarization component is coming, so you can get interference pattern inline, very robust. The one thing number 2 was saying. This I did long ago. Then exicons, non-diffraction, you see lenses. So for conventional, for example, conventional exicons are diffracting. There is a big limit that numerical aperture cannot go 0.75. Also, if you want to have a structured non-diffracting beam, you have to put an extra additional optical component in front of exicon. But thanks to meta optics, you can realize very long propagating beams, which are very important for the lensing perspective because you want larger depth of field, right? So yes, these are several demos. Then in terms of meta holography, we did spin couple. You see where we throw one kind, it's more like an encryption. Oh, okay. Okay, after this I will just go to end. Okay. So it's more like an encryption. You have encrypted something which can only come out. You put, let's say, RCP, you get one information. You put another handedness, you get another information. So I will just skim through. There are lots of like demonstrations we did for polarization optics, and it's like ongoing. Very interesting is tunable. As I was mentioning, even if you build a sheet, if it is passive, it will throw light at one angle. But if you want to steer, it should be tunable, right, in the runtime. So there are several ways to do that, using phase change materials, using liquid crystals, using non-linear like lithium niobates. So this was, you can do all sort of stuff, steering, shaping, holography through tunable meta surfaces. So if Jared, you can play this video, this is like through liquid crystal, you see two different informations. It's just like you change the voltage, you see, you have two information, you just change the voltage, blink of an eye, you can get different informations, and this was actually for a gas sensor, which was like yes or no from the symbol. So if there is some hazardous level of gas, liquid crystals orient themselves in a way that you can tell. Next. Okay. Similarly, again, such kind of tunable meta holograms, and this I would like to demonstrate, and then can you? First, I want to show you this. This is in our lab. So this is source, and this is meta surface, and this is receiver. Now you look at the angle. You look at the angle. So if it is standard Snell's law, the wave was supposed to come this way, right? You are throwing it at angle, it needs to go that way. But unfortunately sound is not there. So what this guy was doing, if you go a little bit back, slightly back, yeah, maybe somewhere in the middle. Okay, now you see, instead of coming this way, it is going that way. And this is very important for like beam steering. And also, this is reconfigurable intelligent surfaces, from design to development to control circuitry, everything we did in our lab with one other collaborator. Yes, on same footstep, that was microwave. So this is Wi-Fi. So there is upcoming technology that is Li-Fi. So what's the advantage of light? We already have lights in our room everywhere. So if we can steer beams, so let's say we have 10 users, and you see, you can steer beam, you put some sticker on top of a lamp, you can use this light for actually communication, indoor communication, high data rate. And for that, you really need tunable stuff, because people are walking. It's more like steering the beam and then sensing the position, because you see, we from the room, it's not only we stand or sit, we also move. So once we move, that beam should follow you, right? It should be sensed. So this kind of thing is very interesting. You can throw indifferent and then you can steer. I think I will stop here. This is like a kind of research output, and I will tell you, for in last 8 years, while staying in Pakistan, in developing countries, so this is like a real demonstration. If you have a will, there is a way. You can do it. So this is recently we got a big funding for this nanomatter materials design for the National Center, which is inaugurated recently, and I'm PI of this lab. And I think, and then in terms of you see outreach, and we do all such kind of stuff, and I will be very happy that there is an optical chapter in this university, and there are several other people. We get along with each other for the service of community as well. So science is something, you see, we all are here. So this is my message will be, we join hands, science for peace and harmony beyond religious and territorial boundaries, and the things where we can collaborate, we can work together to develop novel theories to break the limits, smart design and optimization tools, device level innovation, smart system level integration and development, technology readiness. So any of things you are interested in, we are very open and will be very happy to talk about. Thank you very much.
I think it's time for questioning.
Sorry, I took a bit of more time, but
thank you for the wonderful presentation. So my question is related to applying metamaterials to solar material. Is it it's really impossible, or if it is possible, then how far is it implemented?
Oh, yes. Yes, there is one thing that is known as STPV, solar thermophotovoltaics, where you want to harvest maximum of solar energy for a, you see, at a very high level. For example, for current, solar efficiency is limited by this Schottky limit, which is like 25% and so. What this kind of meta absorbers, you can design such kind of meta absorbers which are really broadband, which can absorb all of the spectrum, solar spectrum, and then you see another, it depends, you absorbed it and then you want to have a photo PV cell, right? PV cell for the conversion of that energy into electrical energy. Now each PV cell has a different band gap, and then you can have another, you see, such kind of meta surface based design which can, you see, tune the band gap. It can do the radiations, black body radiation for that particular band which is compatible with that PV cell. Yes, this is like pretty much possible, but obviously it's not at a technology level scale, it is prototype level stuff.
Yeah, because of time, I think we can go to the next speaker, and you can always reach out to Professor Kasim for any question, because he's still around if you have another question. Our next speaker is Professor Silvania Pereira from Netherlands. I think she spoke to us yesterday, and today she will have another talk on analysis of coherent optical systems. Professor Silvania is in the area of optical metrology, for particle detection and nanostructure characterization, and therefore I take this opportunity to welcome Professor Pereira to talk to us. Thank you.
Okay, can you hear me? Okay, today I would like to continue a little bit, one more subject I would like to treat here, which is continuation from what we did yesterday. But then I would like to go for some applications and also for some work I do, which is related to Fourier optics, just to show that with Fourier optics you can do a lot of interesting applications. So one subject I would like to look is called apodization. So apodization means that yesterday we saw that, okay, you have an object, you illuminate the object, you have a lens, and then from the lens, you go and look for the image plane, right? This is the very simple image system. So apodization means that when you go from the object to the lens, the same thing, remember the slit, that this spatial frequencies will spread around in space, right? And then they come to the lens, and the lens will combine everything to the image plane again. So it makes a copy of your object. But my object can have very special features, and these special features, which has like details for the object, they can be spread in space with these different spatial frequencies. So apodization means that when the light arrives to the lens, I may choose to block or to change some components of those spatial frequencies. And doing that, I can modify the image. So it's something that you can do. And why do you want to do that? It depends on what application. For example, two examples. Suppose you want to soften the edges of the pupil to suppress ring effects in the image. Ring effect means that, remember that the sports peripheral has rings around, yeah? And for some image application, you don't want that. You don't want those ring effects. So, but the ring comes because the aperture is hard. And remember, we had everything 1 and then 0, right? But I can soften that. So if I soften that, I can change this ring effects and make a more smooth image. Other thing you can do is the inverse apodization. So means that create more weight to the edge of the pupil. Yeah, so block the center of the pupil and let only like a ring of light going through the image system. So I would do that. So if you think about the spatial frequencies, mean that I'm eliminating all the low spatial frequencies and only leaving the high spatial frequencies. And this is interesting because you can manipulate the image you are seeing. So suppose you want to detect edges of objects, so then you do the second one because you are only interested in the edges, not the whole object. You are only interested where the objective ends, for example. And that is very interesting for some applications of like looking at a different look at different like boxes or so, and you want to know just the size of the box or where the box ends. You're not interested in what is in the box, but only when the box ends. So this kind of thing. So there are these two are examples, but remember that you can do anything in this plane, yeah, because by intelligent block some frequencies. So basically this is the apodization. So the first apodization is like you make some sort of a Gaussian beam. So you in the aperture where the lens is, you block like with a smooth transmission function. You block the edges. Yeah, so you make the amplitude be higher in the center and slowly less amplitude in the edges. So you make some sort of filter which has a transmission that follows this plot here instead of this one. So what happens is that you see this one, these big lobes here are the lobes that you see in this logarithmic scale, just to amplify, so it's not like that, but are the lobes that you see if you have the hard aperture. So when you put the soft aperture, see the lobes are suppressed a lot. Yeah? So this is logarithmic scale. So this way you have less problems with these rings. So this is one example. So the second example, then you can look what happened in the optical transfer function. That I said, okay, the optical transfer function will be, if I do this in the pupil, I have to add that in my diffraction integral and then look again how these frequencies will pass my imaging system. So remember the last time the unapodized was like some sort of a line going to 0. And the apodized means that the low frequencies will be a little bit better. You'll see a little bit better, but the high frequencies you lose. Yeah, because you are softening the edges. The edges is where the high frequencies are. Yeah? So in this way, you are doing is that you are losing a little bit of information of the high frequencies of the image, but you are improving a little bit the low frequencies of the image. The other one is that this kind of apodization, which means that you enhance or you block the center. You see, you have a transmission function which goes to 0 in the center. So all the low frequencies you have very, very low transmission, and the high spatial frequencies you have high transmission. Yeah? So in this way, you see what happens. Now you have your transfer function, which this was the normal one. So you lose a lot in the low frequencies, but then you gain in the high frequencies, you see? So the details, the very border of the object, the high frequency components are higher now. So if you are interested only in seeing that, you do this kind of apodization. So there are many things nowadays you can calculate. You can calculate what kind of frequencies you want to, like what happens if I suppress some frequencies. You take the Fourier transform and see how it looks like our image. So I just wanted to show that this kind of manipulations can be done in images, and they are used for like when you want to inspect objects, or when you are interested in only some pictures, not the image as would be the object, but you enhance some, and you can do that everything optically. And it's different than on a camera where you take a picture and then you're going to do a lot of processing. You can do that already while you are taking the picture. So that's the importance for industry if you need something to be done fast. You work only by putting a certain aperture in your lens. Okay? I think that is what, that's what I wanted to say this last part. So can you go to the other one? Okay. So now I go to some applications, because okay, now you know, you have learned a lot about Fourier optics, image formation, and modulation transfer function. So you know that, okay, from an image, when you illuminate, you propagate, you have this information spread in space, and then you recombine with a lens to make your image, right? But now I will show some application, which is thanks to the technology from today, we can do a lot of new things that we could not do some decades ago. And so as I said, when you have your object goes to your lens, and the lens will make a phase transformation, remember, and is blocked by the diameter of the lens, and that will go propagate again to the image plane, form the image. But what happens is if I don't use the lens. Yeah? So let's say, and that's called lensless imaging. So lensless imaging is a relatively new field, and it needs the computer. So you cannot do only optically, but there are advantages because you don't need the lens. So all the problems you have with lenses, maybe you can eliminate in some applications. So the idea is that you have the light in, you illuminate your object, and you let it propagate some distance, and you record the diffracted field. That's all. That's your experiment. And so what I say is that, okay, I know the relation between object and diffracted field because they are in this integral. This Fourier transform integral. I know what it is. The only thing I don't know when I record the field is the phase of the light, because I only record the intensity. Yeah? So what I see is not, I cannot just do the inverse Fourier transform. I cannot take just the square root of the diffracted field and take the inverse Fourier transform. It's not going to work because the phase is lost when I measure that. So there are two ways. Either I can measure the phase. If I measure amplitude and phase, then I can do it. Inverse Fourier transform. I get my object back. But if you suppose you don't have, you want to make it cheap, you only have the intensity. So what you do is back propagation. So you take this picture and then you propagate it back, yeah, with your propagation integral, diffraction integral, but then inverse Fourier transform. Then when you arrive at your object ends somewhere, right? Because your object is not infinite. Yeah? So let's say object has a certain size. So everything that is outside the object, I block. I make 0. And I only consider what is inside the object. Now, the object is not bigger than the object, so I have to keep these borders of the object. And then what you do is, again, for the propagation of this new field that I have. Then, when you come here, you also look at your diffractive field, and you go this iteratively many times, until you converge. And there are algorithms to do that. Many of them are open source, you can just download. And this is what you see. So that is, well, this you cannot see very well. This is just a practicum from my students. So what we have there is an object, transmission object, illuminated with a laser, and record the diffracted field at a certain distance in the camera. One thing I need to know is the distance. The distance should be very well measured, so you measure as good as possible, because of course for each distance my diffracted field will be slightly different. But let's say the diffracted field looks like this. This is just what is recorded in the camera. So the experiment is done. Now you go to the computer and you start your algorithm. And then you get like, this is the reconstruct object. Yeah, it's a bit like in a different angle, but you see the reconstruct object, and this was the original object. So, so you see, of course, this is a very simple lensless imaging, one picture. There are more advanced ones, so that you record in different angles and add them in your algorithm. Some people do many of them, like I don't know, 10 or so. Because as you, of course, if you do more angles, your reconstruction will be better. But yeah, I wanted to show that just this very simple example, you already obtain an image without having any lens. Okay. Then I like to go to what I do in my work, because I use metrology for surface inspection. And surface means mostly for wafers and for the semiconductor industry. So everybody has a smartphone, and you are glad that your smartphone is not very costly, because if you think about the whole technology which is inside your smartphone is a very, very complicated technology. So you may ask yourself, how come that this is so cheap? Yeah? Because, you know, it's very complicated if you look at in the computer how everything is there. And that is thanks a lot to optics, because to make the computer cheap, you use just this image system we are talking about. We have an object, which is the printed circuit I want to have. I let it propagate to a lens. I make the image on the wafer. And on the wafer, I have a layer of photoresist. I expose this photoresist, develop the photoresist, and then, okay, lots of the chemical process, and I make my computer chip. And because of that, because it's so simple, and you can make it very fast, very cheap, that your smartphone or your computer can be sold so cheap. But one step which is very important, which also contributes to make the whole process cheap, is the control. So it's the quality control. Because when you print something, you don't know if your print is good or not, right? And then if you cut the wafer in those little pieces, make your IC, integrated circuit, put in the housing, and go to test it, and then you find out, oh, it doesn't work. Then you have to go back again, well, what's going on with the machine that printed that in the first place, right? And that's very costly. Yeah? Think about all those steps that you have to go to all the way to the testing the chip, and they say, oh, something went wrong, go back. So the industry didn't want to do that. No, they want to test something while you are exposing. And so we need a technique to look at what is being printed on site while it's being printed. And so what they do is that they print some test targets all around the wafer, and the test targets are just gratings, okay? Just gratings. The same type of grating we saw in the practical, okay? So the idea is that if I can characterize the grating on site, I can already tell whether the process is good or not. Then I say, oh, if it's not good, say stop. Something is wrong, then I'm going to look what is wrong, okay? And that will use also the Fourier plane, because as I told you, you can measure the period of your grating by just looking at the screen and measuring the spots, so the distance between the spots. I can infer the period of the grating, right? I told you that, and if you do it, you really get quite close to the period that the grating really is. But I don't need to take the grating, go to the microscope and look and everything. And there is more because we have, so what you do is that we send light into these printed gratings, which are tested in the wafer. Look at the orders here, and we don't look only at the position of the spots because we need to know much more about the grating, not only the period. So what we need to do, no, I don't want to do this. We want to do the height of the grating. We need to do how big is this pitch of the grating, the period, and the sidewall angles of the grating. Because think about these are like if you think it like wires, you want the wires not to be close to each other, you want not rounded. There are a lot of things that you want to characterize. So we need more information than only looking at the distance of the 2 points. What we do is that we send two polarizations. One is perpendicular to the grating, one parallel to the grating, record the difference in intensity of those orders with the two polarizations, combine all those information, and then reconstruct the parameters of the grating. But actually the measurement is just like this. It's just shine the light, look at the diffraction orders, record them, and go again to the computer and work on the computer. So that's the idea. So the reflected signal depends on the incident light properties, which we can characterize very well before we start. Yeah? The physical gratings, physical property, that's what you want to know. And it depends on the wavelength I use, so I can use one or two more wavelengths. The angle of incidence also depends, and the polarization, which can be parallel or perpendicular to the grating. And then the physical properties of the grating, which is the real thing we would like to achieve. Material we know, but the other things is the printed grating that we want to know. So these are the parameters the industry says, I want to know this. Yeah? So make a measurement and tell me what is the period, what is this mid CD, so in the middle here how big it is, what's the height, and what are the sidewall angles of the two walls. Okay? So these are the requirements. So once they know this, they can say, okay, this is good enough, we can continue. Otherwise, we're going to stop with the process. So this is the setup we have in our lab. This is a clean room because, of course, the wafer is very clean, so we cannot have too much contamination. And but you see that it's just like an old microscope. Yeah, so we just adapted an old microscope. You have light coming in from top, going to the grating, and you will look at the scattered light. Yeah, so in the Fourier plane in a camera. That's all. So you have a camera, beam splitter, and the lighting, which is just a helium neon laser. So we have this reconstruction. Yes. So this was our reconstruction. So the mid-CD is 563 nanometers plus minus 2 nanometers. The height is 116 nanometer plus minus 1 nanometer. The sidewall angle is 89 plus minus 3 degrees. And well, bias is something else, I don't need that. And then, okay, we have to test whether our setup is good enough. So we go to the electron microscope. So we take that grating, go to the electron microscope, see how good the grating is. The electron microscope cannot measure the height of the grating, only looking for the top if I don't want to break the grating. So we measure with the electron microscope 562 plus minus 4 nanometers. So you see that our measurement is very close to the real, well, if I can believe that electron microscope really has like 1 nanometer precision, it's very close to the real value. And the height is 116 plus minus 1 nanometer. And with the AFM, atomic force microscope, which you can look at the topography of a sample, is the same number. Yeah? AFM is a little bit more error, but we got exactly the same number. Sidewall angle, we measure 89 plus minus 3. That was not possible with the SEM without breaking the sample. We didn't want to do that. And the FM you cannot do because the wall is too high. And then the FM cannot do that. So you see that with this relatively simple setup, we can fulfill these wishes of the industry to characterize those gradients in line and in a very fast way. Another thing is that even before you start measuring anything, you want to know whether your surface is contaminated. Because if there is too much contamination, because can be because when the wafer comes into the site, some contamination can take place. This will also be a loss when you print the circuits, because all this place where it's contaminated, the chip will not work, has to be thrown away. So first they want to know, okay, how many particles per area do you have? Is that reasonable or not? If too many particles, then they stop, go clean, go do something else before they start, right? And here we also use the Fourier plane, so also the scatter light. So we take light in, so you know that if there is anything here, if there would be nothing, just a very plain surface, I would only see the beam being reflected. So if there are some like contamination, there will be some scattered light here. And I go to the Fourier plane and I look at that. I look at this crazy scattered light. In this way here you do a little bit different because you scan. Because then when you scan, what you see, what I'm looking is only the changes in the Fourier plane. I'm not interested in the exactly what is happening in each place, but I want to see whether by scanning here, I see changes in the Fourier plane. And if there are changes, that means, oh, there is some contamination going on there. And the particle is not very, the surface is not really clean. And so that's applications not only for the semiconductor industry, but for plastic-based components like plastic-based OLEDs, which are light sheets that make light, and plastic solar panels, and plastic electronics. Electronics are based on plastic, not on silicon. So this is what we get. So when we scan scan like a confocal microscope, we scan like a raster scan like this. So every time there is a particle, you see that there are some changes in the, this is not an image, this is just the changes in the scattered field. But you see that there are like things going on, and they are not all the same size. They are not one-to-one to the size, but we need to calibrate. And we use convolutional neural network to do that, to classify how big are the particles, because they want to know is that how big they are and where are they. And so here is an example of a sample where there's 40, 50, and 60 nanometer particles. And we can classify the three of them. So you see the difference in diameter is very is likely, only 10 nanometers apart. And but the signal of the scattering is different enough that we are able to classify and say, okay, there are so many 40 nanometer particles, so many 50, so many 60, and so on. So we can map the contamination of the surface. And this setup looks pretty much the same as I showed you. Then we want to know, okay, how small can we go? So can we measure very small particles? Because this is already very much beyond the diffraction limit, but the scattering there's no diffraction limit, really. So we are only limited by noise. So we made like by purpose, like photoresist cubes of 25 by 25 by 25 nanometer, fabricated with E-beam on a silicon wave. So here are just markers, but in those corners here are the particles. And you see that, well, maybe you cannot see, but they are quite visible with 4 dB signal to noise ratio, 25 nanometer photoresist cubes. And if you go to the SEM, you can measure the exactly diameter, and you can fit, and you can see that is, well, the SEM-C is very strange because it's a ball. It's like I think it's because of the height, doesn't see very well, but you can see that this fits into 25 nanometer. So this is our currently limit, and the limit is because the scattering from the roughness of the surface. So the silicon wafer is very flat, but if you go to really to see how flat, it can be a few nanometers rough, and this gives a little bit of noise when we are doing the measurement. So this is our current limit. Then we have done, it was interesting yesterday, I saw also this off-axis holography, because sometimes you cannot put too much light. I mean, we use always very low light, but suppose we are having a system where you want a very little amount of light to the sample. So what you do is that you put extra beam that interferes with this one, which is a stronger beam. And that just to boost the signal from the noise floor. So in this way, while you are scanning here, we move this beam and we make fringes. Yeah, so because every time I have a line here, there is a certain distance, and then can be constructive or destructive interference. So the next line will be, the distance will be slightly different. So you have this scattered field plus the fringes superimposed. Okay, so if you look at this, so you see this is a particle there, and the fringes are superimposed. So remember that this is much higher power than this one, can be much higher power. So what you do is you do the Fourier transform, because now you have fringes, your object which has also some spatial frequencies. When you do the Fourier transform, you see that so you see the zero order with some information here, but you see the plus and minus first order, and they also contain information about the particle, right? So what we do is that we only consider one of the first orders and do the inverse Fourier transform. Because now I am eliminating all the background noise that we had because of the low frequency noise from the experiment. So in this way, I think it's not showing here, but I had another. But this is the result. So we are improving almost 10 dB. So here is the particle. As a pity, because this was the without this, but the without is very noisy. We could almost not see. But this was improvement of 10 dB by just eliminating everything that was in the low frequency region. Same way I told you, attenuation. So if you eliminate the low frequency region, you are only looking at the high frequency, high spatial frequencies, and then you can see the particle much better with respect to the background. So this is something that we have done, and we envision this in applications where you have to put very low laser power here. But now was like less than a microwatt going into the sample. So now we changed that setup, which was in the clean room that I showed you, to a very compact setup, because that is easier to bring to the companies and put the whole instrument online, in line with the process. So now we have a 3D printer setup, which is a monolithic setup. So monolithic is like just like a sandwich. So if you open, you put your components in place, and then you close again, and then they don't move. So they are very robust. So I can go travel around, and they are very robust. And we have done. This is a simple setup for not too small particles, because otherwise it becomes too. But we can measure like 100 nanometer particles easily with this setup. And so you see that here the laser is a laser pen, so it's just something like this. And we have a D splitter, and we go here, we use a DVD objective, which is 0.65 numeric aperture. So we don't need a big objective, just we shine the light into the sample. Back to the D splitter, there is a camera here just to locate, and we have a detector here that look at the differences as we scan. We look at the difference in the far field. This has been designed and built by students, by mechanical engineering students, which work together with the optics students, and then each one they do what they are good in. And so finally we came up with an interesting design, very compact, very robust, and it works very well. So finally this can be really extremely cheap, because there are no very expensive components here. So the other applications we are thinking is because we are like already in the order of 30 nanometers, and we think with this holography, Ofax holography, we could go even better. There could be application in detection of virus and bacteria, because you can go very small now, and it can be interesting. Like for example, if you want to know there's some virus contamination in some surfaces or something. Contamination of air pollution at the levels is smaller than 100 nanometer, because many particle detections they go up to 100 nanometer, but not beyond the under 100 nanometer. But that is this ultrafine dust that we don't see, but maybe it's bad for our health. So maybe that can be interesting, because we can measure less than 100 nanometer. And the other one is also microplastic is in sea and river water. So it's thought that we think about taking samples from water, let it dry, and then see whether there are like microplastics. Because our technique is also, we don't care about low contrast, because since we are only, we have some sort of phase sensitivity, because there is the light that is non-scattered with the one that is scattered, they interfere, because everything is a coherent system. So we think that microplastics usually are very difficult to measure, because there is no contrast with the water. They are about the same index of refraction, you don't see them. And especially when they become very small. It becomes very small particles, you don't see anything. But they might be important for the fishes, for everything. So these are applications that we are thinking about, and yeah, I don't know where we go, but we will see. So I would like to end here. If you need more information, if you want the copies of the articles, there are some open positions, visit possibilities. You can also always contact me. And of course, I am glad to help you. And if you have any question about my technique and all what we do here, just let me know. And I'm open for the questions.
Questions?
What's the smallest size of surface you've been able to analyze using your technique?
The size of the surface?
Yeah, the size of the impurities on the surface.
I don't say the size of the surface.
Yeah.
Yeah. At the moment, we only look at small samples within the wafer, not the whole thing. But we are working on a parallel system of a parallel beams, and then we hope to be able to scan the whole wafer. Yeah. That is still ongoing work. What I show you here is small circles. But we can already do 1 by 1 centimeter without any problem, but of course to scale to a big surface we need parallel system.
Any other question? Yeah, it appears that there are no other questions, but let me just ask one.
Yes.
And you talked about defects when printing the circuit, the wafer. And so how do you mitigate on that, those defects? In other words, how flat is the wafer has to be?
I don't understand the last thing. What did you say?
The surface where you are printing your circuit,
Yeah.
how flat is it supposed to be so as to mitigate on the defects? Because if, for example, you print and then there are defects, then the circuit is not going to work.
Yeah.
So how flat is this supposed to be? Because once you are imaging, then the image has to be very clear for proper printing.
Yeah, usually the industry, they have the tolerances and they say how many particles per square centimeter. And if there is more than so many particles, then it's not good. But usually nowadays the systems are so good that you only see like a couple of particles maybe in a square centimeter. Only like a couple. But sometimes there could be more. So if there is a big contamination, they want to know. A little bit of contamination they can live with. But it's usually the industry gives the specification. We only measure, we only say how much, but they say whether it's good or not. Yeah. It depends a little bit what kind of circuit you are printing. Yeah. For example, for solar cells, the tolerance are much better because the circuits are bigger for solar cells. So they don't care about the very, very small particles or the amount of particles. But for integrated circuits, because they have many very fine structure, then they do care about contamination. Yeah. And if they lose too many, then they cannot sell cheap anymore. Yeah. Then the price will go high. Yeah. Yes. No.
Yeah, thank you for the good presentation. I have a question on the lens-based image.
Yeah.
When you do a diffraction on the object, and then you are recording the CC, but then you are also doing back propagation.
Yeah.
What are you using to do the back propagation?
Inverse Fourier transform. Inverse Fourier transform. So the Fourier transform is equal to the minus ikx, the inverse is equal to the plus kx. So it's all this. It's very simple. Because the propagation between the x to fx or fx to x is just Fourier transform, either direct or inverse.
Is there any physical device?
Hmm?
Is there a device doing that, or?
Well, you can do that optically, but we do with the computer. We just do with a fast Fourier transform in MATLAB or Python. You just do with the computer. So if you have your 2D image, you do the fast Fourier transform in the computer. Then you get your diffracted field, and then you can also do the inverse Fourier transform to get back to the image. As I said, because we have only intensity, we don't have the phase, so the back Fourier transform is not going to be exactly the same as the image. So we need an iterative algorithm to converge to the image. But that means that when you make the support of your object.
Question?
So thank you for that wonderful presentation. If we go the kind of applications you are thinking for this lensless imaging system. So I'm wondering, in terms of the setup, for example, if you are doing this for microplastics.
Sorry?
Microplastics,
Yeah?
will you have the sample like in a cuvette, or you have to put it in a surface and let it dry?
We are thinking about putting a surface, but there is work where they detect particles just passing by the focus field, but that's not so easy. I mean, you have to have many probes. I don't know how to do, but in our case, if we put the sample let it dry, we can inspect. That's the way I'm thinking to do. Yeah. Because the idea is for each, like a certain sample of amount of water, how many classical parts are there. That's the idea. And I'm talking all to the sub-wavelength classical particles, because otherwise you can see them with the microscope.
Another more question?
Question? Are there questions in the Zoom? No? No? Okay.
Yeah, I think if there are no questions, then it is the time for us to go for lunch. We can stop it at this point, and then we can still interact more. They are still here, and can now go for lunch.
So we go for lunch, then immediately we finish lunch, we come here. We will divide you on how you go to the lab. Thank you.
So you don't want anything that is reflective on your hands, not even a watch, because other.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, some for inspiration, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac Lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issue. This is our physics and chemistry lab, where most practicals happen, including tests on materials and present research findings to scientists, ensuring safety and quality standards are met. This is our laser and optics lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our radio. We have our own radio station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you hot shows. This radio has greatly helped students acquire communication skills in readiness to join national and international radio stations.